Have you ever stopped to consider what is actually happening when you feel the warmth of the sun on your skin? It feels instant. It feels immediate. You step out of the shadows, and there it is, a gentle, golden touch that seems to wrap around you without a moment's hesitation. It is perhaps the most familiar sensation in the human experience, a comfort that has greeted every generation of our ancestors since the first eyes opened to the morning sky. But if you could slow down time, if you could peel back the layers of reality and see the universe as it truly is, you would realize that this simple moment of warmth is actually the final act of an epic journey that defies imagination. That soft light washing over your hand is not a single continuous stream, but a bombardment of tiny, discrete packets of energy, messengers from the deep past that have traveled across a void so vast it breaks the human mind to contemplate it. We call them photons, and right now, as you sit here, you are being visited by trillions of them. In every single second, in every blink of an eye, numbers of these tiny particles so large we have no names for them are streaming into your retinas, crashing into your skin, and bouncing off the walls around you. They are the most abundant thing in the universe, yet they are also the most mysterious. They have no mass. They do not experience time. To a photon, the moment of its birth and the moment of its death are the same instant. And yet, for us, they are the clock keepers of the cosmos. They are the only reason we know anything at all about what lies beyond your own small atmosphere. Let us pause for a moment and think about the speed of this arrival. We are taught in school that light travels at a speed limit, a cosmic maximum that nothing can exceed. But knowing the number and feeling the reality of it are two very different things. Light moves at exactly 186,282 miles per second. That is a number that slides off the tongue easily, but try to visualize it. In the time it takes you to snap your fingers, a mere fraction of a second, a beam of light could travel around the entire circumference of the Earth 7.5 times. It is a velocity so extreme that for all practical purposes here on Earth, it appears infinite. When you flip a switch, the lamp turns on instantly. When the sun rises, the light floods the valley without delay. But the universe is not a room, and the sun is not a lamp. Our star sits 93 million miles away from us. That is a distance so great that a commercial jet flying at full speed without stopping would take nearly 20 years to cross it. Yet light, moving at its incomprehensible velocity, crosses that abyss in just 8 minutes and 20 seconds. This creates a strange and beautiful paradox that we live with every day, but rarely acknowledge. We never see the sun as it is. We only ever see it as it was. When you look up at that blinding disk in the sky, though please, never look directly at it. You're looking at a ghost. You are seeing the sun of 8 minutes ago. If the sun were to suddenly vanish, to simply blink out of existence right now, we would not know. We would continue to see it shining, feel its gravity holding us in orbit, and bask in its warmth for another 8 minutes and 20 seconds. We would be living in a past that no longer exists, blissful in our ignorance, until the darkness finally arrived to catch up with the truth. But this 8-minute journey across the vacuum of space is actually the easy part. It is the victory lap. The true story of the light that is hitting your hand right now begins long before it left the surface of the sun. It begins deep inside, in a place of crushing darkness and unimaginable pressure. This is the core of our star, a nuclear furnace where the density is 150 times greater than water and the temperature soars to 27 million degrees Fahrenheit. Here, under the weight of the entire star pressing down, hydrogen atoms are smashed together with such violence that they fuse into helium, releasing a tiny burst of pure energy in the process. This is the birth of a photon. It is born in violence, a spark of gamma radiation created in the most extreme environment within trillions of miles. You might think that because it travels at the speed of light, this newborn photon would instantly shoot out of the sun and race toward Earth. But the core of the sun is not like empty space. It is a crowded, chaotic, suffocating soup of particles. It is so dense that a photon cannot travel more than a tiny fraction of an inch, sometimes as little as a millimeter, before it slams into a charged particle, usually a proton or an electron. Imagine trying to run through a dense forest, but the trees are spaced only inches apart. You take a step and you hit a tree. You bounce off, turn a different direction, take another step and hit another tree. You bounce again. You turn again. You are moving as fast as possible, but you are going nowhere. This is the life of a photon inside the sun. It is what physicists call the random walk. The photon is absorbed by a particle, then spat back out in a completely random direction. It might move slightly outward toward the surface, or it might be sent straight back down toward the core where it started. For the photon, this is a purgatory of collisions. Bounce, absorb, emit. Bounce, absorb, emit. It happens billions upon billions of times. The photon loses energy with every interaction. It starts as a high-energy gamma ray, deadly and powerful. But as it fights its way out, slowly migrating from the crushing core to the radiative zone, and then to the convective zone, it is gradually stretched and cooled. It shifts from gamma rays to X-rays, then to ultraviolet light. And here is the number that truly humbles us. This process takes time, a lot of time. While the flight from the sun to Earth takes only 8 minutes, the journey from the center of the sun to its surface can take anywhere from 100,000 to 170,000 years. Think about that for a moment. The light that is touching your face this morning was not created this morning. It was created before the dawn of human civilization. It was born in the fusion fires of the core when Homo sapiens were still sharing the earth with Neanderthals. It was fighting its way through the dense plasma of the sun's interior while our ancestors were painting inside caves and learning to shape stone tools. It was slowly, painfully bubbling toward the surface while empires rose and fell, while glaciers retreated, while the pyramids were built, and while the modern world was constructed. For 100,000 years, that energy was trapped, pinballing through the darkness of the star, desperate to escape. It is an ancient traveler. It carries with it the memory of the deep primordial forces that power the cosmos. And then, finally, after those millennia of struggle, the photon reaches the photosphere, the visible surface of the sun. Suddenly, the density drops. The crowd of particles thins out. The path ahead clears. For the first time in its long, torturous life, the photon is free. It launches itself into the void. It accelerates to that cosmic speed limit, 186,000 miles per second. It races past Mercury, a scorched and cratered world. It flies past Venus, shrouded in its thick, choking clouds. It crosses the cold, silent vacuum, traveling perfectly straight, perfectly true, carrying the energy it has held on to for 1,000 centuries. And then it hits a blue marble. It punches through the thin layer of nitrogen and oxygen we call our atmosphere. It might scatter off a molecule of air, contributing to the blue of the sky, or it might shoot straight down, through your window, through the lens of your eye, and strike the retina at the back of your skull. There, in a biological miracle as complex as the star that birthed it, the photon transfers its energy to a chemical molecule, triggering an electrical impulse that races to your brain. And in that moment, your mind constructs an image. You see light. You feel warmth. We tend to think of light as something simple, a background utility that helps us navigate our day. But every single photon is a survivor. It is an ancient relic that has endured 100,000-year odyssey just to end its existence in your eye. It has traveled from the most hellish place in the solar system to the most delicate structure in the human body. When you close your eyes and feel the sun, you are not just feeling heat. You are feeling the heartbeat of the star itself. You are touching the result of nuclear fusion that happened before history began. You are connecting with the cosmos in the most intimate way possible. The boundary between you and the star dissolves. The energy that was once inside the sun is now inside you. It becomes part of your warmth, part of your vision, part of your consciousness. But if light is a particle, a thing that travels and hits us, what does it look like? If we could freeze one of these photons in mid-flight, somewhere between the sun and the earth, and hold it in our hand, what would we see? Is it a tiny marble of light? Is it a vibrating string? Is it a wave in an invisible ocean? This is where the story gets stranger, because the more we try to look at the photon, the more it refuses to be pinned down. We ask it, "Are you a particle?" And it behaves like a bullet, striking a target in a single, precise location. We ask it, "Are you a wave?" And it flows like water, bending around corners and interfering with itself. It is the ultimate shapeshifter. It is a ghost that can pass through glass, but bounce off a mirror. It has no mass, yet it can push a solar sail. It takes up no space, yet it fills the universe. As we embark on this journey into the heart of the photon, we have to be willing to let go of our common sense. We have to leave behind the world of solid objects and predictable paths. We are entering the quantum realm, a place where the rules of reality soften and blur. We are going to ask what is hidden inside this tiny packet of light. Is there a structure? Is there an internal mechanism? Or is it, as some physicists suggest, a fundamental point with no dimensions at all, a speck of nothing that somehow carries the energy of everything? The light fading in your room as evening falls is a mystery waiting to be solved. It is a messenger that has seen the beginning of time and will witness the end of the universe. It is the only thing we can truly see, and yet it remains the one thing we cannot truly comprehend. So tonight, as the stars come out, those distant suns sending their own ancient messengers across even greater voids, let us begin our descent into the rabbit hole. Let us strip away the layers of the visible world and chase the ghost in the machine. We have felt the warmth. We have measured the speed. Now, we must look inside. What is a photon, really? And what does its existence tell us about the nature of the reality we think we inhabit? The answers, as we will find, are far stranger and far more beautiful than we could have ever dared to imagine. Have you ever sat by the edge of a still pond in the quiet hours of the morning and tossed a single pebble into the glassy water? You watch as the disturbance radiates outward, perfect concentric circles expanding in a hypnotic rhythm, gentle ripples that travel across the surface until they brush against the reedy banks. Now, imagine you throw two pebbles at once. The circles expand, but where they meet, they do not bounce off each other like billiard balls. They pass through one another. In some places, the peaks of the waves combine to create a higher crest. In others, the peak of one fills the trough of another, canceling it out completely, leaving the water perfectly flat. It is a dance of addition and subtraction, a fluid geometry that we call interference. It is beautiful, it is intuitive, and it is how we understand the nature of waves. For centuries, this was how humanity understood the nature of sound, of water, and, we believed, of light. But what if I told you that the universe is playing a trick on us? What if the light that illuminates the page of a book or the screen of your device is not just a wave washing over you, but also a rain of tiny, solid bullets? And what if it is neither, but something that sits in the uncomfortable silence between two realities, waiting for you to look at it before it decides what to be? As we drift deeper into the mystery of the photon, we must confront the most famous and unsettling puzzle in the history of physics, the duality that shattered our confidence in a solid, predictable world. To understand this, we must travel back in time, away from the high-tech sensors of the modern era, to the candlelit study of a man named Thomas Young in the very first year of the 19th century. The year was 1801. The world was different then, quieter, slower. Science was not yet a massive industrial enterprise. It was often the pursuit of gentlemen philosophers working in the stillness of their own homes. Young was a polymath, a man whose mind wandered across disciplines like a traveler exploring a new continent. He looked at the debate that had raged since the time of Isaac Newton. Newton, the giant of physics, had insisted that light was made of particles, tiny corpuscles shooting through space. It made sense. Light travels in straight lines. It casts sharp shadows. It bounces off mirrors. It feels distinct and direct. But Young had doubts. He felt that light behaved more like the ripples on that pond. So he devised an experiment of elegant simplicity, one that you could almost replicate in your own living room with a piece of cardboard and a sharp knife. He took a beam of sunlight, that ancient traveled light we spoke of before, and let it pass through a barrier with two tiny parallel slits cut into it. Behind this barrier, he placed a screen to catch the light that made it through. Now, pause and ask yourself what you would expect to see. If light were truly made of tiny particles, like microscopic sand grains being sprayed at the wall, you would expect to see two bright lines on the screen directly behind the slits. Most of the particles would be blocked, and the ones that passed through the openings would travel in straight lines to hit the target. Two slits, two lines. Simple, logical, predictable. But when Young looked at the screen, he did not see two lines. He saw a pattern that defied the logic of solid matter. He saw a series of bright and dark bands, a zebra crossing of light and shadow stretching out far wider than the slits themselves. Bright, dark, bright, dark. It was a pattern of interference. It was the signature of waves. Just like the ripples on the pond, the light passing through the two slits had spread out, overlapped, and danced with itself. Where the waves synchronized, they created bright light. Where they clashed, they created darkness. In that quiet room in 1801, Thomas Young seemed to have proven that the universe was fluid. Light was a wave. The debate was settled. The cosmos was a vast ocean of energy, and light was simply the vibration traveling through it. For over 100 years, this was the truth. It felt comfortable. It felt right. But the universe is rarely content to let us rest in certainty for long. As the 20th century dawned, the mystery deepened. New phenomena began to appear that the wave theory simply could not explain. When light hit certain metals, it didn't just wash over them. It knocked electrons loose with the sharp, sudden impact of a collision. It behaved once again like a particle. Albert Einstein, in his genius, realized that light had to be quantized. It had to come in discrete packets. He called them quanta, we call them photons. So, we returned to the double-slit experiment, but this time with modern technology and a deeper question. We decided to be sneaky. We decided to fire the photons one by one. Imagine the precision of this. We tune our light source down until it is so dim, so gentle, that it emits only a single photon at a time. Click. One photon launches. Click. Another follows. We let them travel through the double slits and hit the detector screen on the other side. If they are particles, single, lonely travelers moving through the dark, surely there can be no interference. A single photon cannot ripple. It cannot overlap with itself. It has no partner to dance with. It must go through the left slit or the right slit. It must hit the screen like a tiny bullet, leaving a single dot. And indeed, that is what happens at first. One dot appears, then another, then another. It looks random, like raindrops falling on a dry pavement. But then, we let the experiment run for an hour. We let thousands of these lonely photons make their journey. We step back and look at the cumulative pattern formed by all those individual dots, and what we see makes the hair on the back of our necks stand up. The dots have not formed two bands. They have formed the interference pattern. They have recreated the waves. Let that sink into the silence of your mind. How can this be? Each photon was alone. It left the source, traveled through the void, and hit the screen without ever interacting with another photon. Yet, somehow, each individual photon knew about the other slit. It behaved as if it had gone through both slits simultaneously, interfered with itself, and then decided where to land based on the probability of a wave. It is as if the photon is a ghost that dissolves into a fog of possibilities, exploring every path, every option, every reality, only to solidify back into a particle the moment it touches the screen. This is the heart of the quantum mystery. It suggests that the solid reality we perceive, the chair you sit on, the device you hold, the walls of your room, is actually built on a foundation of fuzzy probabilities. Before a photon is measured, it does not exist in a specific place. It exists in a superposition, a state of being everywhere and nowhere at once. It is not a thing. It is a likelihood. But the story gets even stranger. The universe, it seems, is shy. It does not like to be watched. Physicists, baffled by this behavior, decided to peek behind the curtain. They placed a sensor right next to the slits to see which one the photon actually went through. They wanted to catch the ghost in the act. They wanted to know, did you go left or did you go right? So, they turned on the detector. They fired the photons one by one. The detector beeped. Left, it said. Then right. Then left. The measurement worked. We knew exactly where the photon went. We had forced it to confess its path. But when we looked at the screen at the back, the pattern had changed. The beautiful, mysterious interference bands were gone. In their place were two simple, boring stripes. The moment we watched, the moment we asked the question, the photon stopped behaving like a wave and started behaving like a dull, solid particle. It was as if the mere act of observation forced the universe to make a choice. The wave function collapsed. The infinite possibilities vanished, leaving only a single, concrete reality. This is the observer effect, and it opens a door to questions that border on the metaphysical. Does the universe exist in a definite state when no one is looking? Or is the cosmos a vast, flowing ocean of potential that only hardens into reality when consciousness, or at least a measurement, interacts with it? Think about the light from a distant star, a star that died 1,000,000 years ago. Its photons have been traveling across the universe as expanding waves of probability, passing through dust clouds, bending around galaxies, existing in a state of suspended animation. For 1,000,000 years, they were nowhere and everywhere. And then, tonight, you looked up. You turned your gaze toward the heavens. And in that instant, those waves collapsed. They ended their journey on your retina. They became real because you witnessed them. In a very gentle, very quiet way, this suggests that you are not just a passive spectator in the universe. You are a participant. Your observation, your interaction with the light, is part of the process that weaves the fabric of reality. The world is not a stage that was built before you arrived. It is a performance that requires an audience to become defined. As we lie here in the dark, contemplating the nature of the light that allows us to see, we realize that the photon is a bridge between two worlds. It belongs to the world of the very small, the quantum realm, where magic is real and logic is fluid. But it also constructs the world of the very large, the macroscopic reality of sunsets and shadows and familiar faces. It is the messenger that carries information from the quantum fog to the solid ground of our perception. But what happens inside that fog? If a photon is a wave of probability, what is waving? It is not water. It is not air. It is a ripple in the electromagnetic field, a fundamental fabric that permeates every inch of space. And this field is not empty. It is alive with potential. When we talk about the core of a photon, we are searching for something that might not exist in the way we understand existence. There is no hard kernel inside. If you were to zoom in on a photon, magnifying it trillions of times, you would not find a tiny spinning ball. You would find disturbances. You would find oscillating fields of electricity and magnetism, dancing at right angles to each other, self-propagating, eternal. Imagine a rope stretching infinitely long. If you flick one end, a wave travels down the line. The wave is real. It carries energy. It moves. It can hit things. But the wave is not a separate object from the rope. It is a shape. It is a motion. The photon is a shape in the fabric of the universe itself. It is the universe humming a specific note. And just like a musical note, it can harmonize, it can clash, and it can fade. But unlike a sound that needs air to travel, the photon needs nothing. It brings its own road with it. The electric field creates the magnetic field, and the magnetic field creates the electric field. They pull each other forward, step by step, inch by inch, traversing the vacuum. It is a self-sustaining cycle of creation, a perpetual motion machine that was wound up at the beginning of time and has never stopped spinning. This duality, this refusal to be just one thing, is what allows light to do the miraculous things it does. Because it is a wave, it can squeeze through the tiny pupils of your eyes and spread out to paint an image of the entire world on your retina. Because it is a particle, it can strike the chlorophyll in a leaf and knock an electron loose to start the process of photosynthesis, feeding the entire planet. It is soft enough to wrap around a flower petal, yet hard enough to push a comet's tail away from the sun. The photon is the ultimate diplomat. It negotiates the space between the void and the matter. It travels through the emptiness without changing, but the moment it touches something, a gas molecule, a mirror, a human eye, it transforms. It gives up its life to deliver its message. The energy it carried for 1 billion years is transferred, absorbed, and the photon is gone. It ceases to exist as light and becomes heat, or chemical energy, or an electrical signal in a brain thinking thoughts about photons. So, the next time you see a shadow, look closely at its edge. It is not a sharp, perfect line. It is fuzzy. It is a blur. That blur is the light bending, diffracting, behaving like water flowing around a rock. It is a whisper of the wave nature of reality, visible right there on the pavement. And when you feel this sun, remember the particle, the tiny hammer of energy striking your skin. We are surrounded by this dual magic. We are bathed in a sea of particles that are also waves. We are walking through a universe that is both solid and fluid, defined and undefined. And at the center of it all is the photon, the enigmatic carrier of the electromagnetic force, holding the secrets of quantum mechanics in its non-existent heart. But if the photon has no mass, and it is just a ripple in a field, how does it know where to go? How does it choose the path of least time? How does it explore the universe to find the quickest route to your eye? This brings us to another layer of the mystery, one that involves the very structure of space and time. Because for a photon, as we whispered earlier, time does not pass. It does not experience the journey. For the photon, the birth in the star and the death in your eye are touching. The universe, to a beam of light, is 0 distance wide and 0 seconds old. In the next chapter of our journey, we must try to imagine the universe from the perspective of light itself. We must leave our heavy, slow, time-bound bodies behind and try to ride the wave. What does the universe look like when you are moving at the speed of causality? What happens to the concepts of before and after when you are the thing that defines time? As we drift deeper into this cosmic dream, let the interference patterns of your own thoughts settle. Let the waves smooth out. The particle and the wave are one. The observer and the observed are one. And in the silence between the pulses of light, there is a hidden universe waiting to be found. To understand the true nature of a photon, we must now attempt the impossible. We must step out of our own skin, shed the weight of our biology, and try to inhabit the mind of a beam of light. This is a journey that requires us to leave behind the most fundamental scaffolding of our lives, the ticking of the clock. We are creatures of time. Our hearts beat in a rhythm, our cells age, our thoughts flow from one moment to the next in a steady, unstoppable river. We measure our existence in seconds, years, and epochs. But for the photon, the entity that allows us to see the clock face, time is a meaningless concept. Imagine for a moment that you are an astronaut in a ship capable of miraculous speeds. As you sit on the launch pad, your watch ticks at the same rate as the watch of your friend standing on the ground. But as you ignite the engines and accelerate, a strange and beautiful law of the universe begins to take hold. Albert Einstein taught us that space and time are not separate stages, but a single, woven fabric. And just like a vehicle moving across a map, you have a limited budget of speed. You are always moving through this fabric of space-time at a constant velocity, the speed of light. Right now, sitting in your chair, almost all of that motion is being used to travel through time. You are hurtling toward tomorrow at the maximum possible rate. You are moving through space very little, so your progress through time is rapid. But as your ship accelerates through space, you must steal from your budget of time. The faster you move across the universe, the slower you move through the hours. If you could reach 99% of the speed of light, you would watch stars be born and die in what felt like mere days to you, while millions of years passed for the universe outside. You would become a time traveler, slipping into the future by slowing down your own internal rhythm. Now, take this to its ultimate limit. What happens if you use all of your motion to travel through space? What happens if you hit the cosmic speed limit, 186,282 miles per second? If you pour 100% of your velocity into spatial movement, there is nothing left for time. The budget is empty. The clock stops. This is the reality of the photon. From the moment it is born in the violent fusion of a star to the moment it dies on the retina of your eye, exactly 0 time passes for it. We look at the Andromeda galaxy, 2.5 million light-years away, and we say that the light took 2.5 million years to reach us. We imagine the photon struggling across the void, aging, enduring the eons. But for the photon itself, the journey was instantaneous. It was born in Andromeda and absorbed on Earth in the same singular frozen moment. The birth and the death are touching. To a photon, there is no during. There is no wait. There is only here, and then there. This changes everything about how we perceive the vastness of the cosmos. We feel small because the universe is so large, because the distances are so terrifyingly deep. We look at the dark gaps between the stars and feel a sense of isolation, knowing that even a radio message would take lifetimes to cross the divide. But light does not know this isolation. Light knows only connection. For the photon, the universe is not a vast empty room. It is a point of singularity where all places are connected instantly. And it gets even stranger. Einstein also taught us about length contraction. As you move faster, the space in front of you effectively shrinks. The distance you have to travel becomes shorter. If you were moving at the speed of light, the length of the entire universe in the direction of your travel would shrink to 0. The photon does not experience distance. To a beam of light, the universe has no width. It is a 2-dimensional reality. The starting line and the finish line are the same line. So, when you look up at the night sky, you are witnessing a paradox. You are seeing a history that is ancient to you, but immediate to the messenger. The starlight that touches your face is a bridge that collapses the dimensions of space and time into a single point of contact. The photon is the needle that stitches the universe together, pulling the distant past of a galaxy into the present moment of your perception, making them one. This concept, the speed of causality, suggests that light is not just a traveler. It is the ruler by which reality is measured. It is the cosmic metronome. Nothing can happen, no information can spread, no cause can lead to an effect faster than light can connect them. If the sun were to disappear, gravity would not release us instantly. The Earth would continue to orbit the empty spot for 8 minutes. The darkness and the lack of gravity would arrive together, traveling at the speed of light. The now that we experience is really just a bubble of causality, defined by how fast light can reach us. There is a profound melancholy in this, but also a great beauty. It means that we are forever trapped in our own local time, always seeing the universe as it was, never as it is. We can never know the true now of the universe. By the time we see a star explode, it has been gone for 1,000,000 years. We are always looking at ghosts. We are historians of the sky, reading the archives of the cosmos written in ancient light. The present moment of the distant universe is forever hidden from us, locked away behind the speed limit of light. But if we flip this perspective, it becomes a message of intimacy. Because light does not experience time or distance, every photon is a direct, uncorrupted link to its source. The light from the Big Bang, the cosmic microwave background radiation that fills the space between the stars, has been traveling for 13.8 billion years from our perspective. But for those photons, the fires of creation are still burning right now. When we detect them, we are directly touching the primordial heat of the universe's birth. We are connected to the beginning of everything by a particle that has never known a single second of separation from its origin. This is the silence of the photon. It is a silence that speaks of an eternal present. In the frantic, noisy rush of our human lives, where we worry about the future and regret the past, the photon offers a different wisdom. It exists in the forever now. It does not worry about the journey, because the journey does not exist. It only knows the connection. But the universe is not just empty space for light to glide through effortlessly. The path of a photon is not always a straight line. As we have learned, space is a fabric, and like any fabric, it can be stretched, twisted, and warped. There are heavy things in the dark, massive stars, clusters of galaxies, and the invisible monsters we call black holes. These objects have mass, and mass tells space how to curve. When a photon, traveling its straight and instant path, encounters a curve in space-time, it must follow it. It is like a marble rolling across a trampoline that has a bowling ball sitting in the center. The marble wants to go straight, but the surface itself is bent, so the marble curves. This is gravity. Gravity is not a force pulling on the light. Gravity is the shape of the road the light must travel. This bending of light leads to some of the most mind-bending illusions in the cosmos. A massive galaxy cluster can act like a giant, imperfect lens, a gravitational lens. It captures the light from a galaxy hiding far behind it, light that should have missed Earth entirely, and bends it back toward us. It magnifies it, stretches it into arcs and rings, and sometimes creates 4 or 5 copycat images of the same distant object. We look at the sky and see a mirage, a trick of gravity that allows us to see further and deeper than we have any right to. And then there are the places where the curve becomes a cliff. There are places where gravity is so intense, the warping of space so extreme, that the road for the light curls back in on itself. These are the event horizons of black holes. Here, the struggle of the photon reaches its tragic conclusion. A particle that has traveled for billions of years, surviving the void, avoiding every obstacle, might find itself skimming the edge of this abyss. If it flies too close, the straight line it is following twists into a circle. The photon becomes trapped in orbit, circling the darkness forever, a prisoner of geometry. It is still moving at the speed of light. It cannot move at any other speed. But it is going nowhere. It is running on a treadmill of curved space, and if it crosses the line, if it falls 1 millimeter too close, the path points only inward. The light, the fastest thing in existence, the messenger that connects the universe, is silenced. It falls into the singularity, and its energy is added to the dark. This interaction between light and gravity is the dance that shapes our view of the heavens. It is a delicate balance. Light wants to flee, to expand, to illuminate the void. Gravity wants to pull, to contract, to hide the secrets in the dark. Every star you see is a temporary victory of light over gravity, a ball of plasma held up by the pressure of the photons trying to escape. But what happens to the information carried by that light when it falls into a black hole? Is it lost forever? Does the universe forget? This question haunts physicists. It touches on the very nature of reality and the laws of thermodynamics. If a photon dies in a black hole, does its story end? Or is there a way for the ghost to escape the machine? As we drift in this meditative space, thinking about the zero-time existence of light, we start to realize that the universe is far more fluid than our senses tell us. We see solid objects and empty space. Light sees a connected web of events. We see a ticking clock. Light sees a single frozen sculpture of space-time. Perhaps the peace we feel when we look at the stars comes from this subconscious understanding. We are sensing the timelessness of the light. We are bathing in a stream of energy that knows no age. In a world where everything decays, where flowers wilt and mountains crumble, the photon is an immutable constant. It is the one thing that never grows old. So let the concept of now expand in your mind. Imagine the light filling the room not as a stream of bullets, but as a static, glowing web connecting you to the lamp, to the walls, to the sky outside. You are woven into this web. You are part of the geometry. You are an anchor point for the timeless light. In the next chapter, we will follow the photon into the most colorful and vibrant part of its journey. We have talked about its birth, its speed, and its bending. But we have not yet asked why the world is beautiful. Why is the sky blue? Why is the sunset red? Why are the leaves green? We will explore the secret language of color, which is nothing more than the photon singing in different keys. We will discover how a slight change in energy transforms a deadly gamma ray into a comforting, warm glow, and how the invisible rainbow hidden in white light paints the reality we cherish. The universe is not just black and white. It is a canvas, and the photon is the brush. Have you ever stood in a room filled with crystal glass as the morning sun pours through the window, fracturing the white light into a dozen dancing rainbows on the opposite wall? It is a moment of pure, simple magic. We look at the red, the orange, the violet, and we feel a sense of joy, a connection to something playful and vibrant in the universe. But what if I told you that this rainbow is not an addition to the light, but a dissection of it? The colors were there all along, hiding in the invisible unity of the white beam, waiting for a prism, a raindrop, or a piece of glass to unlock their secret code. In this chapter of our journey, we will listen to the song of the photon. We will discover that the universe is painting with a palette far vast and far more strange than our eyes can ever see, and that what we call color is actually the rhythm of energy vibrating across the cosmos. To understand color, we must return to the idea of the photon as a wave. Imagine the open ocean again. You have seen the giant, rolling swells that travel for miles between crests, the lazy, slow-moving giants of the deep. And you have seen the choppy, frantic ripples whipped up by a sudden gust of wind, the waves that jitter and splash with nervous energy. Photons are exactly the same. They are all made of the same stuff, ripples in the electromagnetic field, but they do not all ripple at the same speed. Some are lazy, some are frantic. And this speed, this frequency of vibration, is what determines the energy they carry. It is what determines their color. If a photon vibrates slowly, with long, languid wavelengths that could stretch across a football field, we do not call it light. We call it radio. These are the gentle giants of the spectrum. They are passing through your body right now, carrying the songs of your favorite station, the data for your phone, the signals from distant satellites. They are photons, just like the ones you see. But their energy is so low, their touch so soft, that your eyes cannot register them. They are ghosts to our biological senses, yet they fill the air with a silent cacophony of information. Now, tighten the wave. Make it vibrate faster. shorten the distance between the crests. The photon gains energy. It becomes a microwave, capable of spinning water molecules to heat your food. Tighten it further, and it becomes infrared, the invisible warmth you feel radiating from a dying campfire or the body of a loved one. This is the thermal heartbeat of the world, a light we feel as heat but cannot see as color. And then we reach a very specific, very narrow band of frequencies. If the wavelength shortens to between 700 and 400 nanometers, a distance smaller than a single bacterium, something miraculous happens. This is the visible window. It is the tiny slice of the electromagnetic reality that our sun pumps out in abundance, and it is the slice that the chemistry of our eyes evolved to catch. When a photon in the lower end of this visible range hits your retina, your brain whispers, red. It is the color of low energy, of long sunsets, of dying embers. As the frequency climbs, the note gets higher. The photon hums with more energy. Red shifts to orange. Orange brightens to yellow. Yellow deepens to green, the color of life harnessing the sun. Green cools to blue. And finally, at the highest energy our eyes can handle, we see violet, the frantic, vibrating edge of the visible world. Beyond violet, the curtain falls again. The waves become too short, too energetic for our biological sensors. This is the realm of the ultraviolet, the black light that can burn our skin and crack our DNA. Go further, and you find X-rays, photons so powerful they punch right through your soft tissues to reveal the bone beneath. And at the extreme end, the screaming high notes of the cosmos, we find gamma rays, deadly, piercing bursts of energy born in the violent deaths of stars and the crushing maws of black holes. Think about this for a moment. The entire rainbow that you know, every painting you have ever admired, every sunset that has moved you to tears, every shade of every flower in every garden on earth, exists in that tiny, fragile gap between the infrared and the ultraviolet. We are looking at the universe through a keyhole. We are seeing less than 1% of the light that actually exists. The cosmos is awash in colors we have no names for, vibrating with energies we can only detect with our machines. If we could see with the eyes of a radio telescope, the night sky would not be dark. It would be blazing with the glow of ancient gas clouds and the jets of distant galaxies. If we could see in gamma rays, the moon would be dimmer than the sun, but the sky would be punctuated by blinding flashes of cosmic violence. But let us stay here, in the gentle sanctuary of the visible. Let us ask the simple questions that children ask, the questions that profound science often forgets to answer. Why is the sky blue? It is a question so common it feels almost banal, yet the answer is a beautiful dance of physics happening miles above your head. As sunlight crashes into the top of our atmosphere, it encounters a blockade of nitrogen and oxygen molecules. These molecules are tiny, far smaller than a raindrop. When the larger waves of red and yellow light hit them, they barely notice. The red photons, with their long, confident strides, step right over the molecules. They continue straight down to the ground, unbothered. But the blue photons are different. They are smaller, shorter, more nervous. Their wavelength is similar in size to the oxygen and nitrogen molecules. When a blue photon hits a molecule, it doesn't step over it. It crashes, it bounces, it scatters. It gets grabbed by the molecule and flung off in a completely new direction. This is called Rayleigh scattering. Imagine 1,000,000 ping-pong balls being dropped onto a field of large boulders. The balls bounce wildly, flying off to the left, to the right, up, down. This is what happens to the blue light. It enters the atmosphere and gets scattered sideways, spreading out to fill the entire dome of the sky. No matter where you look, away from the sun, your eye is catching a blue photon that has been bounced toward you by a molecule of air. The sky is blue because the atmosphere is playing catch with the high-energy light, refusing to let it travel in a straight line. Now, watch what happens as the day ends. The sun dips toward the horizon. The light must now travel through a much thicker slice of the atmosphere to reach your eyes. It is no longer coming straight down. It is cutting across the curvature of the Earth. The path is longer. The gauntlet of gas molecules is denser. By the time the light reaches you, the blue photons have been scattered away completely. They were bounced out of the beam miles ago, lost to the people living in the time zone behind you. The green and yellow photons, which usually make it through, also start to get scattered out by the sheer distance. Who is left? Who are the survivors of this atmospheric marathon? Only the red photons. Only the long, slow waves that can step over the obstacles, the ones that refuse to be diverted. They are the only ones with the stamina to cross the long horizon, and so the sun turns a deep blood orange, and the clouds catch fire with crimson light. The sunset is simply the survival of the fittest photon. It is the visible proof that the Earth's atmosphere is a filter, stripping away the high notes and leaving only the deep bass hum of the red. This interplay of absorption and reflection is the reason the world has any color at all. A leaf is not inherently green. When white sunlight hits the surface of a leaf, the chlorophyll molecules are hungry. They are evolutionary machines designed to eat light. But they are picky eaters. They love the energy of the red photons. They crave the power of the blue photons. They absorb them greedily, using that energy to tear apart water molecules and build sugar. But they have no taste for green. The green photons are rejected. They bounce off the surface of the leaf and fly into your eye. So, when you look at a forest, you are seeing the light that nature threw away. You are seeing the leftovers. The beauty of a lush green valley is actually a map of rejection. If plants had evolved to absorb green light, which is actually the peak energy of our sun, trees might look black or purple to our eyes. We live in a green world because of a quirk of molecular chemistry that occurred billions of years ago in the first algae. And what about the deep velvet blue of the ocean? Water is a different kind of filter. It is dense. It absorbs light quickly. The first colors to die in the deep are the reds and oranges. Dive down just 30 feet, and blood looks black. The red photons simply cannot push through the water. Their energy is soaked up by the H2O molecules, turning into tiny amounts of heat. The blue photons, with their higher energy and shorter wavelength, can penetrate deeper. They can travel down hundreds of feet before they too are absorbed. This is why the ocean is blue. It is the only light that can escape the watery depths to return to the surface. The abyss, the true deep, is a world of eternal blackness, where no photon from the sun has ever reached. There is a philosophical question hiding here, one that brings us back to the observer. Does color exist out there in the universe? Or is it purely a creation of your mind? Physicists will tell you that the universe contains only energy and matter. It contains wavelengths. It contains frequencies. A photon vibrating at 450 terahertz has a specific physical reality. But red? Red is not a property of the photon. Red is a translation. It is a story your brain tells you about that energy. The universe in its raw state is silent and dark. It is a silent storm of electromagnetic fields. When a photon enters your eye, it triggers a chemical reaction. A signal travels down the optic nerve, a spark of electricity, nothing more. Your brain takes that spark, checks which cell sent it, and then paints a sensation into your consciousness. It creates the qualia of redness. It invents the feeling of warm orange or cool blue. This means that the beauty of a sunset is not happening in the sky. It is happening in your skull. You are the artist. The photon provides the paint, but you provide the canvas and the vision. Without a conscious mind to experience it, a rainbow is just a gradient of radiation. Without you to see it, a flower is just a structure reflecting a specific wavelength. You are the one who turns physics into aesthetics. You are the one who turns energy into emotion. Think about the creatures that share this world with us. A honeybee looks at a dandelion and sees patterns we cannot imagine. Its eyes are tuned to the ultraviolet. It sees landing strips on the flower petals, guiding it to the nectar, markings that are totally invisible to us. To a bee, a garden is a completely different painting, glowing with secret signs and hidden colors. A snake, hunting in the dark, sees the infrared heat of a mouse, seeing color where we see only blackness. A mantis shrimp, with its 16 color receptors compared to our 3, swims in a psychedelic explosion of color that would probably overwhelm the human brain. We are all trapped in our own sensory bubbles, seeing only the slice of reality that our biology allows. We assume our view is the truth, but it is just one channel on the cosmic television. The true reality is a cacophony of all frequencies at once, a blinding, deafening richness that would shatter us if we perceived it all. As you rest in the dim light of your room, look at the shadows again. Notice how they are not just gray, but often tinged with blue or violet. Notice how the incandescent light of a lamp makes the room feel cozy because it mimics the red heavy spectrum of a sunset or a fire, triggering an ancient relaxation response in your primal brain. We are creatures of light. Our moods, our sleep cycles, our hormones, all are tuned to the shifting frequencies of the photons around us. We are entering an era where we are beginning to understand this language of light. We use blue light to keep us awake and warm light to help us sleep. We use X-rays to heal and infrared to diagnose. We are learning to play the instrument of the electromagnetic spectrum, expanding our reach beyond the visible window. But there is a special magic in the visible. There is a reason we find it beautiful. Perhaps it is because it is the light of our home star. Our eyes evolved to see exactly the peak output of the sun. We are tuned to this star. If we lived around a cooler, red dwarf star, our eyes might see into the infrared, and the sky would look forever like a sunset. If we lived around a hot, blue giant, we might see deep into the ultraviolet. We are children of the sun, and our perception of beauty is a direct reflection of the star that warms us. So, the next time you see a color, the bright red of a strawberry, the deep indigo of the twilight sky, the flash of a bird's wing, remember the journey of the frequency. Remember that the redness of the berry is a rejection of red light, a bounce, a game of catch between the fruit and your eye. Remember that the blueness of the sky is a scattering, a chaotic dance of high energy. And remember that the sensation of color is your own private miracle, a moment where your consciousness reaches out to touch the vibration of the universe and gives it a name. We have followed the photon from its birth in the core, through its timeless flight across the void, to its scattering in the atmosphere. Now, it is time for the final and most mysterious leg of the journey. The photon is about to enter the temple of the body. It is about to pass through the lens of the eye and strike the retina. In the next chapter, we will explore the biological machinery of sight. We will look at how a single particle of light can trigger a cascade of chemistry that results in a thought. We will stand at the threshold where physics becomes biology and where energy becomes perception. The photon is knocking at the door. Let us open it and see what happens inside. We have followed the traveler across the void. We have watched it escape the crushing gravity of a star, race through the silence of deep space, navigate the chaotic scattering of the atmosphere, and survive the filtering of the elements. Now, the photon arrives at the most delicate and miraculous destination in its entire existence. It approaches the biological threshold where energy is transmuted into meaning. It is time to enter the eye. Consider the bravery of this organ. The human body is mostly shielded, wrapped in layers of skin, protected by hair and cloth, guarded against the radiation of the cosmos. But the eye is an exception. It is the only part of the central nervous system that is exposed directly to the world. It is a piece of the brain that has pushed its way out of the skull, shedding its armor to stand naked and vulnerable against the storm of light. It is a wet, fragile sphere sitting in a bone cave, willing to catch the fast-moving particles that the rest of the body hides from. As the photon approaches your face, it first encounters the cornea. This is the transparent shield, the window of the temple. It is a living structure, yet it has no blood vessels, for blood would block the view. It breathes oxygen directly from the air, a rare and intimate connection between tissue and atmosphere. The photon passes through this shield without pausing, but its path is bent slightly. The cornea is a lens, the first focusing element, guiding the wild, scattered light toward the center. Next, the photon dives into a small ocean. It enters the anterior chamber, filled with the aqueous humor, a clear, watery fluid that nourishes the eye from within. It swims through this pool in a fraction of a nanosecond, heading toward the gatekeeper. This is the iris, the colored curtain that gives your eyes their beauty, but its purpose is strictly utilitarian. It is a muscle, a biological aperture that expands and contracts to control the flood. If the sun is bright, the iris cinches tight, protecting the inner sanctum from being overwhelmed. If the room is dim, like it is now as you rest, the iris opens wide, begging for every scrap of light, inviting the shadows in. The photon slips through the pupil, that black hole in the center of the color. To an observer, the pupil looks black because the light that goes in rarely comes back out. It is a one-way tunnel. Once the photon crosses this threshold, there is no turning back. It is committed to the journey into the interior. Behind the pupil sits the lens. This is a marvel of biological engineering, a crystalline structure that can change its shape. Tiny muscles pull on it, flattening it to see the distant mountains, or relaxing to let it bulge so you can read the words on a page. The lens grabs the photon and bends it one final time, sharpening its trajectory, aiming it with exquisite precision. But in doing so, it performs a strange trick. It flips the world. The image of the tree, the face, the stars, everything is projected onto the back of your eye upside down. You are physically seeing an inverted reality. It is only the brain, in its wisdom, that flips it back right side up, correcting the geometry so that the floor remains beneath your feet. After the lens, the photon enters the vast dark chamber of the vitreous humor. This is the main body of the eyeball, filled with a clear, jelly-like substance. It is a quiet, stagnant ocean. The floaters you sometimes see, those little drifting shadows in your vision, are the debris of your own biology casting shadows on the retina. reminders that you are looking through a living medium. The photon flies through this jelly, straight and true, approaching the final wall. And then, impact. The photon strikes the retina. This is the screen at the back of the theater, a thin, paper-like tissue lining the inside of the eyeball. It is one of the most complex structures in the known universe. In a space no larger than a postage stamp, over 100 million photoreceptor cells are waiting in the dark, standing like a dense forest of biological antennae. They are the rods and the cones, the silent sentinels of vision. The rods are the guardians of the night. They are incredibly sensitive, capable of detecting a single photon, the smallest possible amount of light. They do not see color. They see only the presence or absence of energy. They paint the world in shades of gray, allowing us to navigate the moonlight. The cones are the artists of the day. They are less sensitive, needing a flood of light to activate, but they are tuned to specific frequencies. They are the ones that distinguish the red of the rose from the green of the leaf. When our traveler, the photon, slams into one of these cells, the journey of physics ends and the journey of biology begins. This is the moment of magic. This is the transduction. Inside the photoreceptor cell, there are stacks of tiny disks, and embedded in these disks are millions of molecules of a special protein called rhodopsin. Rhodopsin is a biological trap. It is a protein that is holding a small, crooked molecule called retinal. The retinal is bent like a spring under tension, waiting for a trigger. When the photon hits the retinal molecule, it absorbs the energy. In a time frame so fast it is measured in femtoseconds, quadrillionths of a second, the retinal molecule straightens out. It snaps from a bent shape to a straight shape. This microscopic mechanical shift, this straightening of a single molecule, is the spark that ignites the world. It is a lever that has been pulled. The changing shape of the retinal forces the protein to change its shape, which triggers a chemical cascade inside the cell. It is like a line of dominoes falling. One molecule activates another, which activates 100 more, which closes tiny channels in the cell membrane. The flow of ions, charged particles of sodium and potassium, is suddenly altered. The electrical charge of the cell shifts. The photon has died. It has given up its energy to flip the switch. It no longer exists as light. It has become a signal. A silent pulse of electricity travels out of the photoreceptor, passing to the bipolar cells, and then to the ganglion cells. These cells gather the signals from the forest of rods and cones, compressing the data, enhancing the edges, beginning the process of interpretation before the information even leaves the eye. They bundle their long tails together to form a thick cable, the optic nerve. This cable is the data highway. It carries the electrical codes away from the eye, through the back of the socket, and into the dark, encased wetness of the brain. And here is the profound paradox of sight. The brain lives in eternal darkness. It is sealed inside a bone vault. No light ever reaches the visual cortex. No photon ever touches the gray matter. Your brain has never seen the sun. It has never seen a face. It has only ever seen patterns of electrochemical impulses. The optic nerves from your two eyes meet and cross, mixing the signals from the left and right visual fields, and then dive deep into the brain to a relay station called the thalamus, and finally to the visual cortex at the back of your head. Here, in the darkness, the miracle of reconstruction happens. Millions of neurons fire in synchronized patterns. They take the stream of electrical ticks and start to weave a reality. One set of neurons detects vertical lines. Another detects horizontal motion. Another detects the contrast between light and dark. Another hunts for specific shapes, like the curve of a smile or the angle of a nose. It is a massive, parallel computation, a biological simulation running in real time. Your brain takes these fragmented clues and builds a model. It says, based on these electrical impulses, there must be a lamp in the corner, there must be a sky above, there must be a hand in front of the face. It paints the colors, simulates the depth, and stabilizes the image so the world doesn't shake when you move your head. It fills in the blind spot, the place where the optic nerve leaves the eye, where there are no photoreceptors, making up information to ensure your vision feels complete and seamless. What you are seeing right now is not the world itself. You are seeing the model. You are seeing the story your brain is telling you about the signals it received. You are living inside a simulation created by your own mind, updated continuously by the rain of photons falling on your retinas. This realization is both unsettling and empowering. It means that perception is an act of creation. You are not a passive camera recording reality. You are an active artist painting it. The beauty you see in the world is a collaboration between the physics of the universe and the biology of your consciousness. The grandeur of a mountain range is just rock and geometry until your brain adds the feeling of grandeur. The serenity of a blue lake is just water and reflection until your mind adds the feeling of peace. And consider the speed of this processing. The brain takes about 13 milliseconds to process an image. That is incredibly fast, but it is not instant. It means that you are always living slightly in the past. By the time your brain has constructed the image of the moment has already gone. We are perpetually lagging behind reality, chasing the present, but never quite catching it. But let us return to the darkness of the skull. In this quiet, sealed chamber where no light enters, how does the sensation of light arise? How does the firing of a neuron, a wet chemical event, transform into the subjective experience of brightness? This is the hard problem of consciousness. Science can trace the photon from the star to the retina. It can trace the electrical signal from the eye to the cortex. But the final jump, the leap from chemistry to experience, remains a mystery. We do not know how matter becomes mind. We do not know how the machinery of the brain generates the ghost of the self. Maybe the eye is not just a sensor. Maybe it is a bridge. It is the place where the universe touches itself. The cosmos is made of light and matter. You are made of matter. When the light hits your eye, the circuit is completed. The universe is looking at itself through you. The separation between out there and in here is an illusion created by the skin. In reality, the flow of energy is continuous. The photon that left the sun is the same energy that triggers the neuron, which is the same energy that forms the thought. As you close your eyes now, drifting deeper into relaxation, think about the darkness behind your eyelids. It is not an empty darkness. It is a canvas waiting for light. It is a resting state. Your rods and cones are recharging. The retinal molecules are slowly bending back into their tensioned shape, resetting the traps, preparing for the next photon. The metabolic machinery of the eye is scrubbing away the waste products of vision, feeding the cells, restoring the balance. Vision is work. Seeing is an energetic expense. Your brain consumes 20% of your body's energy, and a huge portion of that goes to processing vision. To close your eyes is to grant yourself a true rest. It is to turn off the data stream, to silence the noise of the photons, to retreat into the peaceful cave of the inner self. But even in the dark, you can see, you can dream, you can visualize. This proves that the light you see is internal. You carry the sun inside you. You carry the memory of every color you have ever seen. The visual cortex can run the simulation without the input of the eye. It can construct worlds that do not exist, painting with the same neural brushes it uses for reality. There is a gentleness in this biological design. The eye is incredibly resilient, yet it needs protection. It washes itself with tears every time you blink, a windshield wiper that clears the dust and keeps the window transparent. These tears contain natural antibiotics, guarding the temple from invasion. The eyelids are the shutters, snapping closed at the slightest threat, faster than you can think. The brow is the overhang, keeping the sweat and rain away. Every part of your face has evolved to serve and protect this precious, vulnerable sphere. We often take our sight for granted. We open our eyes in the morning and expect the world to be there. But every moment of vision is a hard-won victory. It is the result of 1 billion years of evolution, from the first primitive eye spots of ancient sea creatures that could only tell light from dark, to the complex, focusing, color-seeing camera you possess today. It is a legacy of survival. You are the descendant of the creatures that saw the shadow of the predator, that saw the color of the ripe fruit, that saw the sparkle of the water. So, respect the machinery. Honor the complexity. When you look at a simple object, a flower, a hand, a stone, try to see it not just as a thing, but as an interaction. You are bathing it in your attention. You are collecting its photons. You are allowing it to enter your brain and become part of your mind. The photon has completed its physical journey. It has been absorbed. But its information lives on. It has become a spark in the neural web. In the next chapter, we will follow this spark deeper into the labyrinth of the mind. We will explore how vision connects to memory and emotion. Why does the sight of a specific color remind you of your childhood? Why does the light of the moon make us feel lonely or romantic? We will leave the anatomy of the eye and enter the geography of the soul, exploring the invisible connections that turn a visual image into a feeling. The light has entered the temple. Now, let us see how it illuminates the altar. The electrical echo of the photon has now left the visual cortex. It has been processed, analyzed, and assembled into a coherent image of the world. You see the room, the shadows, the texture of the blanket. But vision is not a cold, detached stream of data. If it were, we would be nothing more than biological cameras recording the universe without caring about it. But we do care. We feel. The sight of a particular shade of blue can trigger a sudden wave of calm. The harsh glare of a fluorescent bulb can induce anxiety. The golden slanted light of an autumn afternoon can bring a lump to the throat, a sensation of nostalgia so thick it almost has a taste. In this chapter, we descend from the surface of sight into the deep, ancient caverns of the emotional brain. We explore the geography of the soul, where light ceases to be physics and becomes feeling. To understand this, we must look at the wiring diagram of the human mind. When the optic nerve delivers its payload of information to the brain, the signal does not just go to the visual cortex to be seen. It splits. It takes a detour. A stream of information is sent directly to the limbic system, the primitive, evolutionary core of the brain that governs emotion, memory, and survival. Specifically, it touches the amygdala, the tiny almond-shaped watchman that scans every experience for the threat or pleasure. This happens before you're even consciously aware of what you're seeing, before your intellect says, "That is a sunset." Your amygdala has already tasted the light. It has analyzed the color, temperature, and the intensity. It has recognized the soft, red heavy spectrum of the dying sun and sent a signal to your body. Safe, rest, peace. This is why beauty feels instantaneous. You do not decide to find a landscape beautiful. The feeling washes over you before the thought arrives. It is a visceral reaction, a handshake between the wavelength of the light and the chemistry of your ancestors. Consider the profound connection between light and memory. The hippocampus, the librarian of the brain, is inextricably linked to the visual system. We rarely remember facts in isolation. We remember scenes. We remember the lighting of the scene. Think back to a cherished memory from your childhood, perhaps a holiday morning or a quiet afternoon in a garden. Notice how the light is the primary character in that memory. You can see the way the dust motes danced in the sunbeam. You can feel the specific quality of the illumination. This is because light is the index code for our lives. The brain tags every memory with the lighting conditions of the moment. This is why a specific time of day can suddenly transport you back 20 years. You step outside on a crisp October evening, and the angle of the shadows, the particular violet hue of the twilight, matches a pattern stored deep in your neural web. Suddenly, you are 7 years old again, walking home from school. The feeling of that past self rushes in, triggered by nothing more than the geometry of a photon hitting the atmosphere. We are time travelers, and light is our machine. But there is one specific light that holds a unique power over the human psyche, the light of the moon. Why does moonlight feel so different from sunlight? Physically, it is the same photons. The moon has no light of its own. It is merely a mirror, a rock reflecting the sun's rays back at us. But the mirror is imperfect. The surface of the moon is gray and dusty. It absorbs much of the red and yellow light, reflecting a spectrum that is cooler, dimmer, and more silvery. When this weak, reflected light reaches Earth, it is too dim to activate the color-sensing cones in our eyes. It activates only the rods, those sensitive black and white guardians of the periphery. This is the secret of the moon's romance. Under moonlight, we literally cannot see color. We see a monochrome world of silver and black, of soft edges and indistinct shapes. Our vision becomes fuzzy, dreamlike, impressionistic. We are forced to fill in the gaps with our imagination. The world becomes a mystery again. The harsh, definitive edges of the day soften into the ambiguity of the night. In this silvery ambiguity, we feel a sense of quiet, of solitude, of intimacy. We feel lunacy and love, emotions that thrive in the shadows where the analytical mind cannot see clearly. However, the influence of light goes deeper than emotion and memory. It reaches into the very clockwork of our biology. Buried deep within the hypothalamus, sitting right above the place where the optic nerves cross, is a tiny cluster of 20,000 neurons called the suprachiasmatic nucleus. This is the master clock. It is the conductor of the body's circadian orchestra. For billions of years, life on Earth has evolved under a rhythmic sky. Bright, blue, heavy light in the morning, soft, red, heavy light in the evening, darkness at night. This rhythm is not just a backdrop. It is the metronome of our metabolism, and our eyes have a secret way of listening to it. Hidden among the rods and cones, discovered only recently by scientists, is a third type of photoreceptor. These cells do not help us see images. They are not connected to the visual cortex. They contain a pigment called melanopsin, and they are tuned specifically to the frequency of blue light, the color of the midday sky. These cells are the timekeepers. When blue light hits them, they send a signal straight to the master clock, screaming, "It is day! Be alert. The master clock responds by suppressing the production of melatonin, the hormone of sleep, and boosting cortisol, the hormone of action. It raises your body temperature. It sharpens your focus. It prepares you to hunt, to gather, to think. But as the sun sets and the blue light fades, the signal stops. The master clock whispers to the pineal gland, "The day is done." The valve opens, and melatonin floods the bloodstream. This is the chemical tide of sleep, a drowsiness that is directly orchestrated by the absence of blue photons. This is why the modern world feels so exhausting. We have built machines that emit blue light, our phones, our screens, our LED bulbs, and we stare into them late into the night. We are bombarding our ancient timekeepers with a false signal. We are telling our brains it is noon when it is actually midnight. The master clock becomes confused. The chemical tide is held back. We lie in bed, tired but wired, disconnected from the cosmic rhythm that governed our ancestors. To reclaim our rest, we must respect the photon. We must embrace the darkness, allowing the biology of the night to do its work. Let us also consider the evolutionary history of our relationship with light. For millions of years, darkness was synonymous with danger. The night was when the predators hunted. The night was when the temperature dropped. To be in the dark was to be vulnerable. The invention of fire changed everything. It gave us a way to push back the night. Imagine the first humans gathering around a campfire. This was the first artificial light. It was a small, flickering circle of safety in a vast, hostile world. Inside the circle you could see faces, you could communicate, you could bond. Outside the circle there were only eyes reflecting the flames. This deep ancestral memory is etched into our DNA. It is why a candlelit dinner feels intimate. It is why we are drawn to the fireplace. We are seeking the safety of the circle. We are seeking the warmth that kept the darkness at bay. This association between light and safety, between light and knowledge, is woven into our very language. When we understand something, we say, "I see." We call a smart person bright or brilliant. We have an idea, a word that comes from the Greek root for vision. We speak of enlightenment. We equate the photon with the truth. To see is to know. To be in the dark is to be ignorant. We are phototropic creatures, turning our minds toward the light, just as a sunflower turns its face toward the dawn. But there is a phenomenon where the wires cross, where the senses blend in a beautiful confusion. It is called synesthesia. For some people, light is not just seen, it is heard, or tasted, or felt. A certain shade of orange might taste like apricots. The sound of a cello might appear as a flash of indigo light. This condition reveals the arbitrary nature of our perception. The brain is a dark room where all signals are just electricity. It is only the wiring that determines whether a signal becomes a color or a sound. In a way, we are all synesthetes. We feel that a minor chord is dark. We feel that a yellow room is cheerful. We are constantly translating energy from one sensory language to another, creating a rich, multi-layered experience of reality. As you lie there, visualizing the gentle pulse of the optic nerve, consider the concept of the mind's eye. Where does the light go when you dream? You are in a pitch-black room, eyes closed, yet you can see landscapes, faces, colors. The neurons in your visual cortex are firing in the same patterns as if you were seeing them for real. You are generating your own photons, not physically, but experientially. You are a creator of light. This internal universe is just as vast as the external one. The number of possible neural connections in your brain exceeds the number of atoms in the known universe. You contain a cosmos within your skull, and in this cosmos, light is the currency of thought. Every idea is a spark. Every memory is a shimmer. The consciousness that is listening to these words is a phenomenon of energy, a complex, self-sustaining pattern of bioelectricity that shines in the dark. We have explored the physics of the photon, the biology of the eye, and the psychology of the mind. But we have not yet asked the ultimate question of origin. Where does the light come from? We know it comes from the sun and from the stars. But how? How does a cloud of cold hydrogen gas collapse to become a nuclear furnace? How does the universe switch the lights on? In the next chapter, we will travel back to the source. We will leave the intimate quiet of the human brain and return to the grand, violent, and magnificent scale of stellar evolution. We will watch the birth of a star. We will see how gravity, the great sculptor, squeezes the void until it ignites. We will learn that every photon that has ever touched you is a child of a cosmic struggle between the crushing weight of matter and the explosive power of fusion. We are going to witness the engine of creation itself. But for now, rest in the knowledge that you are a being of light. You are tuned to the stars. Your sleep, your mood, your memories, and your safety are all dances with the photon. You are not separate from the universe. You are a resonator, vibrating in harmony with the energy that fills the void. Let the darkness of the room be a comfort, for it is only in the dark that we can see the stars. To understand the origin of the light that warms your face, we must travel back to a time before the sun existed. We must go to a place of profound silence and unimaginable cold, deep in the velvet darkness between the stars. This is the stellar nursery, a giant molecular cloud drifting through the galaxy like a ghost. It is a vast, sprawling nebula of hydrogen gas and dust, stretching for hundreds of light years. To human eyes it would appear as a void, a patch of sky where no stars shine, a hole in the heavens. But if you could see with the eyes of a radio telescope, you would see it glowing with the faint, cold hum of potential. This is the womb of the cosmos. It is here, in the freezing dark, that the greatest magic trick of the universe is about to be performed, the transmutation of nothing into everything. The cloud is stable at first. The pressure of the gas pushing outward balances the gentle pull of gravity pulling inward. It hangs in a delicate equilibrium, a sleeping giant waiting for a wake-up call. That call might come in the form of a shock wave from a nearby supernova, a ripple in the fabric of the galaxy that nudges the gas, disturbing its slumber. Or perhaps it is just a random fluctuation, a slight drift of density that tips the scales. Whatever the trigger, the balance is broken. Gravity, the patient and relentless sculptor of the universe, seizes the opportunity. Gravity is the weakest of the fundamental forces. A small magnet can pick up a paperclip against the gravitational pull of the entire Earth. But gravity has a secret weapon. It is infinite, and it is cumulative. It never sleeps. It never cancels out. It only adds up. In the dense pockets of the molecular cloud, the hydrogen atoms begin to fall toward each other, slowly at first, adrift, a whisper of motion. But as they gather, their combined mass increases. The gravitational pull grows stronger. The drift becomes a flow. The flow becomes a rush. The rush becomes a landslide. Imagine a region of gas billions of times the size of our solar system collapsing in on itself. As the cloud shrinks, it begins to spin. This is the law of conservation of angular momentum, the same law that makes an ice skater spin faster when she pulls her arms in. The vast, lazy cloud tightens into a swirling disk, and as it compresses, it heats up. The gravitational energy of the falling gas is converted into thermal energy. the center of the cloud begins to glow, not with nuclear fire, but with the heat of friction and compression. It is a protostar, an angry red infant wrapped in a blanket of dust, hidden from the universe, growing hotter and denser by the second. For millions of years, this collapse continues. The core gets smaller, tighter, hotter. The temperature rises to thousands of degrees, then millions. The atoms are packed so closely together that they are stripped of their electrons. They become a plasma, a soup of naked nuclei and frantic electrons. But it is not a star yet. It is still just a ball of hot gas fighting a losing battle against its own weight. Gravity is trying to crush it out of existence, trying to squeeze it down to a single point, to stop the collapse, to turn on the light. The star needs a miracle. It needs to ignite. But there is a problem. The nuclei of hydrogen atoms are protons, and protons are positively charged. Like magnets with the same polarity, they repel each other. The closer you push them together, the harder they push back. This is the Coulomb's barrier, an electric wall that prevents atoms from fusing. According to the laws of classical physics, the temperature in the core of the sun, about 27 million degrees Fahrenheit, is actually not hot enough to overcome this barrier. The protons are moving fast, but not fast enough to crash into each other. They should bounce off. The star should fail. But the universe plays by the rules of the quantum realm. And in the quantum realm, impossibilities become probabilities. Because a proton is not just a particle, it is also a wave. And a wave does not have a precise location. It is smeared out in space. There is a tiny, vanishingly small chance that the proton is not here, but there. There is a tiny chance that it can simply tunnel through the electric wall as if it weren't there. This is quantum tunneling. It is a rare event. For any individual proton, the chance of tunneling and fusing with another is astronomically low. A single proton could bounce around the core of the sun for billions of years without ever fusing. But the sun contains octillions of protons. The sheer number of opportunities turns the improbable into the inevitable. Suddenly, deep in the crushing dark of the core, two protons tunnel through the barrier and touch. The strong nuclear force, the most powerful force in nature, but one with a tiny reach, snaps them together. They fuse. One of the protons turns into a neutron, releasing a neutrino and a positron. They become deuterium. Then, another proton slams into them. They become helium-3. Finally, two helium-3 nuclei crash together to form a stable helium-4 nucleus, spitting out two protons to start the cycle again. In this complex dance of subatomic particles, something profound happens. If you weigh the ingredients, the four hydrogen protons, and then weigh the result, the one helium nucleus, you find a discrepancy. The helium is slightly lighter. About 0.7% of the mass is missing. Where did it go? It did not vanish. It changed. As Albert Einstein revealed with his elegant equation, $2, mass and energy are interchangeable. That tiny sliver of missing mass has been converted into pure energy. It is released as a gamma ray, a high-energy photon. This is the moment of ignition. This is the heartbeat of the star. The energy released by this fusion creates an outward pressure. It is like millions of nuclear bombs detonating every second, pushing out against the crushing weight of gravity. The collapse stops. The star stabilizes. It enters a state of hydrostatic equilibrium. It is a perfect balance between the desire of gravity to crush the star and the desire of the fusion fire to blow it apart. The protostar shakes off its cocoon of dust. A stellar wind blows the remaining gas away, and there, shining in the void, is a new sun. It is a sphere of perfect turmoil, a self-sustaining engine that turns matter into light. This is the source. Every photon that hits your eye, every joule of energy that powers the weather, every calorie in the food you eat, began here in this microscopic act of quantum fusion. The light is the scream of matter being destroyed and reborn as energy. But not all stars are created equal. The universe is a diverse garden. The mass of the collapsing cloud determines the destiny of the star. If the cloud is small, barely massive enough to ignite, it becomes a red dwarf. These are the tortoises of the cosmos. They burn their fuel slowly, miserly. They are cool, dim, and red. But because they sip their fuel so gently, they can live for trillions of years. Every red dwarf that has ever been born since the Big Bang is still shining today. They will be the last lights to go out when the universe grows old. If the cloud is massive, however, it creates a monster, a blue giant. These stars are rock stars. They are massive, hot, and incredibly luminous. They burn through their fuel with reckless abandon. Their cores are so hot, their pressure so intense, that they fuse hydrogen at a frantic rate. They shine with a brilliant blue-white light that can be seen across galaxies. But the price of this brilliance is a short life. A blue giant might live for only a few million years, a cosmic blink of an eye, before running out of fuel and dying in a spectacular supernova explosion. Our sun is a yellow dwarf, a middle-class star. It is not too big, not too small. It is stable. It has been burning for 4.5 billion years, and it has enough fuel to burn for another 5 billion. It is the Goldilocks star, perfect for nurturing life. But there is a deeper connection between you and these stellar furnaces. The universe began with only hydrogen and helium. These are simple, light gases. You cannot build a planet out of gas. You cannot build a bone, or a leaf, or a brain out of hydrogen. Life requires complexity. It requires carbon, oxygen, nitrogen, iron, calcium. Where did these heavy elements come from? They were forged. Inside the core of a star, the fusion does not stop at helium. As a star ages and runs out of hydrogen, gravity starts to win again. The core compresses. The temperature spikes. The star gets desperate. It starts fusing helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. With each step, the star squeezes the nuclei tighter, building heavier and heavier atoms, climbing the periodic table. The calcium in your teeth. It was forged in the dying heat of a massive star. The iron in your blood, the metal that carries oxygen to your cells. It was created in the final moments of a supergiant's life, right before it exploded. The carbon that forms the backbone of every DNA molecule in your body, it was cooked in the belly of a star that died billions of years before Earth was formed. When these massive stars die, they explode, they shatter. They fling these enriched, heavy elements out into the galaxy. These clouds of stardust drift through space, mixing with new gas clouds. And then, gravity begins the process again. A new generation of stars is born, but this time, the cloud is rich with the ashes of the ancestors. This time, there is enough solid material to form rocks, asteroids, planets, and people. So, when we say you are star stuff, it is not a metaphor. It is a literal, physical fact. You are a nuclear waste product. You are the ash of dead stars organized into a thinking being. The atoms in your right hand may have come from a different star than the atoms in your left hand. You are a galactic collection, a mosaic of cosmic history. This realization changes how we look at the light. When you feel the sun, you are feeling the energy of a sibling. The sun is doing what the stars that made you did. It is forging the next generation of elements. It is a cycle of creation and destruction that has been running for 13.8 billion years. And what about the failed stars, the clouds that were too small, that never got hot enough to ignite? They are out there too. We call them brown dwarfs. They are the almost stars, warm but dark, drifting in the shadows. They bridge the gap between giant planets like Jupiter and the smallest red dwarfs. They are reminders of the delicate threshold of ignition. If Jupiter had been 80 times more massive, it would have ignited. We would have lived in a binary star system with 2 suns in our sky. The night would have been rare. History would have been completely different. But we have one sun, one beautiful, stable, lonely star. It sits at the center of our lives, holding us in its gravitational embrace, feeding us with its photon rain. It is a middle-aged star in the prime of its life. It is calm. It is reliable. But it is not eternal. The battle between gravity and fusion cannot last forever. The fuel is finite. The hydrogen will run out. The balance will tip. One day, the sun will change. It will grow. It will turn red. It will swallow the inner planets. The gentle warmth we feel today will become a firestorm. But that is a story for the future. For now, let us appreciate the main sequence, the long, stable summer of a star's life. It is in this stability that life has a chance to evolve. It takes billions of years for simple cells to become complex eyes that can look up and wonder. It takes a calm star to allow that process to unfold. As you lie in the safety of your room, think about the turmoil inside the sun. Think about the random walk of the photon we discussed earlier. That photon was born in the core, in that fusion event. It carries the signature of that violence. But by the time it reaches you, it has been tamed. It has been spread out. The deadly gamma ray has become visible light. The nuclear fire has become a gentle warmth. The atmosphere of the Earth protects us further, filtering out the harsh X-rays and UV rays that the sun still emits. We are cradled in a series of protective layers. The magnetic field of the Earth, the ozone layer, the atmosphere, the distance itself. We are shielded from the raw power of the universe, allowed to enjoy its energy without being destroyed by it. This is the Goldilocks zone, not just the distance from the sun, but the entire configuration of our reality. The strength of gravity, the speed of light, the charge of the electron. If any of these constants were slightly different, stars wouldn't form, or they wouldn't explode to create heavy elements, or they would burn out too fast for life to begin. We live in a universe that seems fine-tuned for the existence of stars, and therefore for the existence of us. So, the light is not just a wave. It is a storyteller. It tells us about the conditions in the core. By analyzing the spectrum of the light, the barcode hidden in the rainbow, we can tell what the sun is made of. We discovered helium in the sun before we discovered it on Earth. That is why it is named after Helios, the sun god. We can look at a star 1,000 light years away and know that it has iron or calcium or oxygen. We can do chemistry across the cosmos. We don't need to go there to know what is there. The light brings the information to us. We are the only species on Earth that knows this. The dog enjoys the sunbeam. The cat sleeps in the warmth. The flower turns toward the light. But only we know why. Only we know about the fusion, the tunneling, the neutrinos, the vast journey. This knowledge does not diminish the beauty. It deepens it. It adds a layer of awe to the sensation. You are touching the heart of a star. You are intimately connected to the nuclear physics of the cosmos. The boundary of your skin is transparent to the energy of the universe. In the next chapter, we must face the inevitable. We have spoken of birth and life. Now we must speak of death. But in the cosmos, death is not an end. It is a transformation. We will explore what happens when the fuel runs out. We will look at the beautiful, ghostly shrouds of planetary nebulae. We will look at the white dwarfs, the diamonds in the sky, and we will look at the ultimate destination of the most massive stars, the supernova and the neutron star. We will see how the death of a star sows the seeds for new worlds, and how the darkness is just a pause between the lights. The silence of the molecular cloud gave birth to the star. The star gives birth to the light, and the light gives birth to the mind that perceives it. It is an unbroken chain, and tonight, as you drift towards sleep, remember that you are part of that chain. You are not just in the universe. You are of the universe. You are the way the cosmos knows itself. We often think of death as a quiet fading, a final closing of the eyes, a retreat into the silence of non-existence. In our human experience, the end of a life is a moment of stillness, a cessation of energy. But in the theater of the cosmos, death is not a silence. It is a scream. It is the most violent, creative, and magnificent event that physics allows. It is an act of generosity so profound that it makes life itself possible. In this chapter of our journey, we must stand witness to the final moments of the Titans. We must look into the face of the inevitable darkness and discover that it is actually a blinding flash of creation. We are going to explore how the death of a star becomes the birth of a world, and how the atoms that beat in your heart were bought at the cost of a stellar apocalypse. To understand the end, we must return to the delicate balance we spoke of earlier, the hydrostatic equilibrium. For billions of years, a star is a stable fortress held up by the pressure of fusion against the crushing weight of gravity. But this fortress is built on a limited supply of fuel. The hydrogen in the core is vast, but it is finite. As the eons pass, the ash of the nuclear fire, the helium, builds up in the center. The fire dims, the pressure drops, and gravity, the patient hunter that has been waiting for 10 billion years, makes its move. When a star like our sun begins to die, it does not go gently into the night. It gets angry. It gets large. As the core contracts under gravity, it heats up, igniting a shell of hydrogen around the dead helium center. This new, hotter burning pushes the outer layers of the star outward. The sun will swell. It will grow to a monstrous size, expanding across the orbits of Mercury and Venus. It will turn a deep, angry red. It will become a red giant. If you were standing on Earth 4 or 5 billion years from now, the horizon would be dominated by a wall of fire. The oceans would have boiled away long ago. The mountains would be melting. The sky would be a furnace. It is a terrifying image, but there is a strange beauty in it. The star is shedding its skin. It is loosening its grip on its own matter. The outer layers of the red giant, held loosely by gravity so far from the center, begin to drift away. They form a gentle wind, a stellar breeze carrying carbon and oxygen out into the void. This is the quiet death. It is the fate of our sun. After the red giant phase, the core will collapse one final time, becoming a white dwarf, a glowing ember of dense carbon the size of the Earth, but with the mass of the sun. It is a diamond in the sky, slowly cooling over trillions of years. But the outer layers, the skin of the star, will continue to expand outward, illuminated by the ultraviolet light of the dying core. This creates one of the most breathtaking sights in the universe, a planetary nebula. Do not let the name fool you. It has nothing to do with planets. It is a ghost. It is a shimmering, colorful shroud of glowing gas shaped like a ring or an hourglass or a butterfly wings, expanding silently into the dark. These nebulae are the art galleries of the galaxy. They are the final breath of a medium-sized star, exhaled in a cloud of fluorescent gas enriched with the elements of life. It is a peaceful end, a slow donation of matter back to the universe. But for the true giants, the massive stars that live fast and die young, the end is not peaceful. It is a catastrophe. Inside a star 20 times the mass of the sun, the fusion process we described earlier does not stop at carbon or oxygen. The crushing weight of the star drives the temperature higher and higher, forcing heavier atoms to fuse. The star burns carbon into neon, neon into oxygen, oxygen into silicon. It is a desperate race against gravity. Each fuel source burns faster than the last. The hydrogen phase lasts millions of years. The carbon phase lasts thousands. The oxygen phase might last only a year. The silicon phase lasts only a day. The star is an onion of fusion shells, a frantic engine trying to hold up the ceiling, but eventually it creates iron, and iron is the killer. Iron is the ash that cannot burn. Fusing iron does not release energy. It consumes energy. It is a thermodynamic dead end. When the core of the star turns to iron, the engine stops. The pressure that has held up the star for millions of years vanishes in an instant. Gravity wins. In a fraction of a second, less time than it takes to blink, an iron core the size of the Earth collapses to the size of a city. It falls inward at 25% of the speed of light. The outer layers of the star, suddenly unsupported, rush inward to fill the void. They slam into the ultra-dense core with unimaginable force, and then they bounce. The shockwave generated by this bounce, powered by a flood of neutrinos, tears through the star. The result is a supernova. It is a word we use casually, but the reality breaks our comprehension. For a few weeks, a single supernova can outshine an entire galaxy of 100 billion stars. It releases more energy in 10 seconds than our sun will release in its entire 10 billion year lifetime. It is a blast of X-rays and gamma rays that sterilizes anything nearby. If a supernova went off within 30 light years of Earth, it would strip away our ozone layer and likely end all life on the surface. But inside this violent furnace, in the chaos of the shock wave, something magical happens. The temperature and pressure become so extreme that they go beyond the normal fusion of the core. Atoms are smashed together with such force that they capture neutrons rapidly. This is the R process, the rapid neutron capture process. It is here, in the heart of the explosion, that the universe creates the true heavyweights of the periodic table. Gold, platinum, uranium, silver. Think about the gold ring on a finger or the silver chain around a neck. That metal was not made in the slow burn of a star's life. It was forged in the violent death of a supernova. It was cooked in a billion-degree shockwave and then blasted out into the cosmos at 10,000 miles per second. Every atom of gold on Earth is a shrapnel from a stellar bomb that exploded before the solar system existed. We value gold because it is rare, but we should value it because it is the artifact of a cosmic tragedy. To create a wedding band, a star had to die. To create the uranium that powers our nuclear plants, a giant had to fall. We are adorning ourselves with the debris of the apocalypse, and it is not just the precious metals. The explosion scatters everything: the carbon, the oxygen, the nitrogen, the calcium, the iron. All the elements the star spent its life manufacturing are suddenly liberated. They are flung out into the interstellar medium, mixing with the cold, dark clouds of hydrogen that are drifting nearby. This is the great cosmic recycling program. The universe begins with simple gas. Stars cook it into complex matter. Supernovae spread that complex matter out. Then, gravity gathers the enriched gas to form new stars and, crucially, planets. You cannot build a rocky planet like Earth out of pristine Big Bang hydrogen. You need the grit. You need the dust. You need the heavy elements provided by the dead generations of stars. Our solar system is a third-generation system. We are built from recycled material, the silicon in the rocks beneath your feet, the iron in the core of the Earth that generates our magnetic field, the oxygen in the oceans. It is all gifted to us by the ghosts of the past. Consider the iron in your blood. Hemoglobin is a molecule with a single atom of iron at its center. This iron atom is the cage that captures oxygen in your lungs and carries it to your brain. Without that iron atom, you cannot breathe. You cannot think. You cannot live. That specific iron atom was once in the core of a massive star. It was part of the dead ash that killed the star. It was at the center of the collapse. It was blasted out in the supernova, drifting through the vacuum for millions of years, freezing in the cold dark. It became part of the cloud that formed our sun. It became part of the molten rock of the young Earth. It cycled through the geology of the planet, through the volcanoes and the oceans, until it was taken up by a plant, eaten by an animal, and eventually found its way into your blood. You are walking around with the heart of a dead star pumping through your veins. The death of the star was necessary for the breath of the human. It is a direct lineage. We are the afterlife of the cosmos. This realization brings a strange kind of comfort. We fear death. We fear the end. But the universe shows us that the end is merely a transformation. If the first generation of stars had not died, the universe would still be boring. It would be just hydrogen and helium. There would be no chemistry, no biology, no complexity. There would be no water, no rock, no life. The violence of the supernova is the price of complexity. The destruction is the prerequisite for creation. And what is left behind? What remains of the giant after the explosion? If the star was massive, but not too massive, the core survives as a neutron star. This is an object that defies belief. It is a city-sized ball of pure neutrons, packed so tightly that a single teaspoon of its material would weigh 1 billion tons. It spins hundreds of times a second, flashing a beam of radio waves across the galaxy like a cosmic lighthouse. These are the pulsars, the timekeepers of the deep sky. The magnetic fields around them are trillions of times stronger than Earth's, capable of ripping atoms apart from miles away. And if the star was truly a monster, if the core is too heavy even for neutrons to support it, then the collapse does not stop. The city shrinks to a building, the building to a grapefruit, the grapefruit to a walnut, the walnut to a point. Gravity becomes infinite. The fabric of space-time is punctured. A black hole is born. We often think of black holes as monsters, as vacuum cleaners that eat everything. But in the context of our story, they are the tombstones of the Titans. They are the places where the star has left the universe entirely, leaving behind only its gravitational ghost. They are the ultimate mystery, the lock on the door of reality that we have not yet found the key to. But even in the presence of these dark remnants, the cycle continues. The gas that was blown away in the explosion drifts on. It cools. It slows down. It mixes with the dust of other explosions. And in the silence of the void, gravity begins to pull it together again. A new molecular cloud forms. A new nebula glows in the dark. and deep inside, a new protostar begins to warm up. But this new star will be different. It will have metals in its atmosphere. It will have a disk of dust around it. And out of that dust, planets will form. And perhaps, on one of those planets, an eye will open and look up at the star and wonder where the light comes from. The story is a circle. We are currently in the middle of it. We are the beneficiaries of the past violence, living in the quiet era of the solar system, bathed in the light of a stable star. But we are also the future dust. One day, the sun will expand. Earth will be vaporized. Our atoms will be returned to the void. We will become part of the planetary nebula, glowing in the dark for a few thousand years, before drifting off to become part of the next star, the next planet, the next life. This is not a depressing thought. It is a liberating one. It means we are not temporary visitors in the universe. We are permanent residents. We are the matter of the cosmos, awake for a brief moment to appreciate the view before returning to the cycle. We are the universe experiencing itself. As you breathe in and out, feeling the rhythm of your own life, remember the rhythm of the stars. Inhale, the gathering of gas. Exhale, the expansion of the nebula. The beat of your heart is an echo of the pulsar. The warmth of your skin is a memory of the supernova. You are small, yes, but you're also ancient. You are vast. You are made of the most precious materials in existence, forged in the most dramatic events in history. In the next chapter, we will shift our gaze from the violent past to the mysterious present. We have talked about the matter we can see, the stars, the gas, the dust, the planets. But astronomers have discovered something unsettling. When we weigh the galaxies, the numbers don't add up. The stars are moving too fast. The galaxies are spinning too quickly. There is not enough visible matter to hold them together. They should be flying apart. Something else is out there. Something invisible. Something heavy. We call it dark matter. It is the ghost in the room. It makes up 85% of the matter in the universe, yet we have never seen it, touched it, or captured it. It passes through you right now as if you were a ghost. In the next chapter, we will walk into the shadows to hunt for this invisible giant. We will explore the skeleton of the universe, the hidden scaffold that holds the galaxies in place, and ask the question, are we the normal ones, or are we the rare, glowing exceptions in a universe made of darkness? Rest now in the stardust that you are. Let the iron in your blood carry the oxygen to your resting brain. Let the calcium in your bones hold you steady. You are a child of the giants, and the giants are watching over you in the silence of the night sky. We have spent our journey so far bathing in the light. We have followed the photon from the blinding nuclear furnace of the sun through the prism of the atmosphere and into the biological miracle of the human eye. We have traced the heavy elements in our blood back to the violent death screams of supernovas. We have constructed a view of the universe that is brilliant, colorful, and vibrant. But I must now ask you to do something difficult. I must ask you to dim the lights. I must ask you to look at the spaces between the stars. We have been admiring the foam on the ocean, the white, frothy caps of the waves that catch the sunlight. But we have ignored the ocean itself. We have ignored the deep, dark water that supports the foam. In this chapter, we walk into the shadows to hunt for the ghost that holds the galaxy together. We are going to explore the mystery of dark matter. Imagine for a moment that you are standing on a playground at night. There is a merry-go-round spinning rapidly in the center. You cannot see the metal structure of the ride because it is painted pitch black. All you can see are small, glowing lights attached to the outer rim, perhaps children holding flashlights. As the merry-go-round spins faster and faster, you expect the children to be thrown off. You know the laws of physics. You know that the centrifugal force should overcome their grip. If the ride spins too fast, the outer edge should fly apart. But, to your amazement, the lights stay put. The children do not fly off. They are moving at impossible speeds, yet something is holding them in. There is an invisible tether, a phantom rope, keeping the structure intact against all the laws of motion. You understand. This is exactly what happened when astronomers in the 20th century began to measure the rotation of galaxies. They looked at the beautiful spiral arms of galaxies like our own Milky Way or the Andromeda Galaxy. They measured the speed of the stars at the center and the speed of the stars at the edge. According to the laws of gravity discovered by Isaac Newton and refined by Albert Einstein, the stars at the edge should be moving slower than the stars at the center. Just like the outer planets of our solar system move much slower than Mercury or Venus, the outer stars of a galaxy should drift lazily in the dark, but they do not. When we looked, we found something that made no sense. The stars at the edge of the galaxy are screaming through space just as fast, sometimes even faster, than the stars near the core. They are moving so quickly that the gravity of the visible matter, the stars, the gas, the dust, the black holes, is nowhere near strong enough to hold them. By all rights, every spiral galaxy in the universe should fling itself apart. The stars should be ejected into the void like stones from a sling. The beautiful spirals should dissolve into chaos, but they do not. The galaxies are stable. They have been spinning for billions of years, maintaining their shape, holding onto their high-speed stars with an effortless grace. This implies a terrifying and wonderful truth. There is more gravity than there is matter. There is an invisible hand gripping the stars. There is a hidden mass, vast and heavy, that surrounds the galaxy like a cocoon, providing the extra gravity needed to keep the carousel from breaking apart. We call this stuff dark matter, but the name is a bit of a misnomer. It suggests that it is like a dark cloud, a shadow that blocks light. But it is not a shadow. It is much stranger than that. If you hold up a piece of dark glass, it blocks the light. If you look at a black wall, it absorbs the light. Dark matter does neither. It is perfectly transparent. It is invisible in the truest sense of the word. Light passes right through it, as if it were not there. It does not reflect. It does not absorb. It does not emit. It does not interact with the electromagnetic force at all. It is a ghost in the machine of reality. And yet, it is heavy. It has mass. It bends space. We know it is there because we can see its footprints. We can see the way it distorts the light from distant galaxies. We can see the way it dictates the motion of the stars. It is like seeing the wind in the trees. You cannot see the air, but you can see the leaves moving. The stars are the leaves, and dark matter is the wind. But here is the number that should make you pause and take a deep breath. When we tally up all the mass in the universe, every star in every galaxy, every planet, every cloud of gas, every black hole, every atom in your body, and every drop of water in the ocean, we find that normal matter, the stuff we can see and touch, makes up only about 15% of the total mass. The other 85% is dark matter. Let that sink in. The universe is not made of atoms. The universe is made of dark matter. Atoms are just a rare spice sprinkled on top, a glowing dusting of glitter on a vast invisible sculpture. We are the anomaly. We, the people made of carbon and water, living on a rock made of silicon and iron, orbiting a star made of hydrogen and helium. We are the exotic, rare exception. The normal state of the universe is to be invisible, cold, and dark. Think about the giant galaxy we discussed earlier, IC 1101. We marveled at its size, its 100 trillion stars, its diameter of 6 million light-years. But what we see through the telescope is just the tip of the iceberg. Surrounding that glowing ball of stars is a halo of dark matter that extends for tens of millions of light-years. The visible galaxy is just a small knot of light in the center of a gargantuan sphere of darkness. The dark matter halo is the true body of the galaxy. The stars are just the bioluminescent bacteria living in the belly of the beast. This invisible substance is the skeleton of the cosmos. In the early universe, long before the first star ignited, dark matter began to clump together. Because it does not interact with light, it could not be blown apart by radiation. It collapsed under its own weight, forming vast invisible filaments, a cosmic web stretching across the void. These filaments are the highways of the universe. Ordinary gas, the hydrogen and helium, was attracted to the gravity of these dark matter strands. The gas flowed along the invisible rivers, pooling in the dense nodes where the filaments crossed. And in those pools, the gas became dense enough to ignite. So, galaxies are not scattered randomly. They are strung like pearls along the necklace of dark matter. Every galaxy you see is nesting in a cradle of this invisible stuff. Without dark matter, there would be no structure. The universe would be a smooth, boring soup of gas. Gravity would have been too weak to pull the atoms together to form stars. There would be no sun, no earth, no you. We owe our existence to a ghost. But what is it? This is one of the greatest, embarrassing mysteries of modern science. We have been staring at the evidence for decades, yet we still do not know what a particle of dark matter looks like. Is it a WIMP, a weakly interacting massive particle? Is it an axion? Is it a primordial black hole? We have built cathedral-like detectors deep underground, buried in gold mines and beneath mountains, to try to catch it. Imagine a tank filled with tons of liquid xenon, pure and still, sitting a mile beneath the surface of the Earth. The rock above shields it from cosmic rays and ordinary radiation. It waits in the absolute silence and darkness. The scientists are waiting for a single particle of dark matter to breeze through the Earth, pass through the rock, and bump into a single nucleus of xenon. Just a tiny nudging, a microscopic flash of light in the tank. That is all they need. They have been waiting for years. The detectors are more sensitive than anything ever built. They are listening to the silence of the universe with an ear pressed to the ground. And so far, nothing. The dark matter passes through the detectors, through the Earth, through the scientists themselves, without leaving a trace. It is a ghost that refuses to be caught. It interacts only through gravity, ignoring the strong and weak nuclear forces that govern our world. This means that right now, as you sit in your chair, there is a wind of dark matter blowing through you. The Earth is moving through the galaxy, orbiting the center of the Milky Way at 500,000 miles per hour. As we move, we plow through the dark matter halo of the galaxy. Trillions of dark matter particles are streaming through your body every second. They do not hit your atoms. They do not trigger your nerves. They pass through the empty space between your protons and electrons as if you were made of mist. To dark matter, you are the ghost. You are the insubstantial phantom that offers no resistance. There is a profound humility in this realization. We tend to think of ourselves as the center of the story. We think that matter means stuff we can touch. But the universe is telling us that our kind of matter, baryonic matter, is just a froth, a byproduct, a minority report. The true universe is a dark, silent ocean that we are floating in, oblivious to the currents. And this ocean is not just a shapeless blob, it is complex. Computer simulations show us that the dark matter halos are lumpy. There are sub-halos, small clumps of darkness orbiting the big galaxies. Some of these clumps might have trapped a few stars, creating dwarf galaxies that we can see, but others might be completely dark galaxies that contain no stars at all. Imagine a solar system with no sun, a galaxy with no light, just a swirling vortex of invisible gravity drifting through the void. It is a terrifying and lonely thought, but entirely possible within the laws of physics. However, dark matter is not just a passive scaffold, it is a lens. Because it has mass, it warps the fabric of space-time. When we look at a distant cluster of galaxies, we often see the light from objects behind it smeared out into arcs and rings. By analyzing these distortions, we can map the location of the invisible mass. We can draw a map of the ghost. One of the most famous examples of this is the bullet cluster. It is a crime scene in the cosmos, a place where two giant clusters of galaxies smashed into each other millions of years ago. When the clusters collided, the hot gas, the normal matter, crashed and stopped, slowed down by friction like two cars hitting head-on. But the dark matter, having no friction, kept going. It passed right through the collision, carrying the bulk of the gravity with it. When we look at the bullet cluster, we see the hot gas stuck in the middle, glowing with X-rays, but the gravity is centered on the two empty regions on either side. The soul of the cluster has separated from the body. It is the most direct proof we have that dark matter is real and distinct from the atoms we know. As we lie here in the dark, let us try to visualize this hidden world. Close your eyes and imagine the room around you. You see the walls, the furniture, the window. Now, imagine that these solid objects are just the glowing highlights of a much denser, invisible reality. Imagine the air is filled with a heavy, silent presence that flows through the walls like water through a net. Imagine that the gravity holding you to the bed is being aided by this invisible hand. The universe is full. It is not empty. The vacuum is not a void. It is a crowded room where the guests are ignoring each other. We are the glowing guests, the loud ones, the ones radiating light and heat. Dark matter is the silent majority, the quiet observers who hold the room together but never speak. This mystery brings us back to the limits of human knowledge. We have named it dark matter, but the name is just a placeholder for our ignorance. It is a label on a box we cannot open. It reminds us that for all our telescopes, all our mathematics, all our pride in understanding the cosmos, we are still like children playing on the seashore, while the great ocean of truth lies all undiscovered before us. But the darkness of the universe has one more secret to reveal. We have talked about the gravity that pulls things together, the visible matter and the dark matter. Both of these are attractive forces. They want to crush the universe down, to slow the expansion, to bring everything back into a single point. For decades, astronomers believed that this was the destiny of the cosmos, that gravity would eventually win, slowing the expansion of the universe until it stopped and reversed, leading to a big crunch. But in 1998, we looked at the distant supernovae, the standard candles of the cosmos. To measure this slowing down, we wanted to see how hard the dark matter was breaking the expansion. And we found something that broke physics again. The universe is not slowing down. It is not breaking. It is speeding up. The galaxies are flying away from us faster and faster every day. The expansion of the universe is accelerating. It is as if someone pressed the gas pedal on the cosmos. Gravity is losing the war. There is something else out there, something that is not matter, not dark matter, not radiation. It is a form of energy inherent to space itself, a repulsive force that pushes the galaxies apart. We call it dark energy. And if dark matter is the skeleton of the universe, dark energy is the growing emptiness between the bones. In the final chapter of our journey, we must face the future. We must look at where this acceleration is taking us. We will explore the fate of the universe in a world dominated by this mysterious repulsive force. We will watch the galaxies drift away until they disappear over the horizon of the visible universe. We will watch the stars burn out one by one. We will watch the black holes evaporate. We will witness the heat death, the time when entropy wins and the universe becomes a cold, dark, and silent sea of nothingness. It sounds bleak, I know, but there is a profound peace in the final silence. It is the peace of completion. It is the silence of a song that has been sung perfectly to the very last note. But for now, stay with the dark matter. Stay with the invisible embrace. Feel the gravity that holds you. Know that you are anchored. The universe is heavy with mystery, and that weight is what keeps us from flying apart. We are held. We are supported. We are not alone in the dark. The darkness itself is a presence, a companion, a structure that has allowed us to exist. We are the light riding on the back of the dark, and the ride is far from over. Take a deep breath. Fill your lungs slowly, feeling your chest rise, your ribs expand, and the space inside you grow larger. Now, exhale. Feel the contraction, the settling, the return to a resting state. This rhythm of expansion and contraction is the fundamental pulse of biological life. We expect things that grow to eventually stop growing. We expect a ball thrown into the air to eventually slow down and fall back to earth. We expect an explosion to dissipate, its energy fading into the silence. For most of the 20th century, this was the intuitive logic we applied to the universe itself. We knew the cosmos began with a bang, a moment of infinite heat and expansion, and we assumed that, like a chest exhaling or a ball falling, the initial energy would eventually fight a losing battle against gravity. We believed that gravity, the great collector, the force we explored in the last chapter that binds the galaxies and the dark matter into a cosmic web, acted as a universal brake. We thought the mutual attraction of every atom in the universe, pulling on every other atom, was slowly dragging the expansion to a halt. The question was not if the universe was slowing down, but how fast. Was there enough gravity to stop the expansion entirely and pull everything back into a big crunch, a reverse Big Bang? Or was the universe too light, destined to expand forever, but at an ever slower, more lethargic pace, drifting gently into eternity like a car running out of gas? But the universe, in its infinite capacity to humble us, had one more card to play, one more ghost to reveal. In the late 1990s, two teams of astronomers set out to measure this deceleration. They turned their telescopes to the distant beacons of the cosmos, the Type 1a supernovae. We spoke of these earlier as the violent deaths of white dwarf stars, because these explosions always happen at a specific mass limit. They always burn with the exact same brightness. They are standard candles, cosmic light bulbs of known wattage scattered across the dark. By measuring how bright they appear to us, we can calculate exactly how far away they are. and by measuring the redshift of their light, how much the light has been stretched by the expansion of space, we can measure how fast the universe was expanding when that star exploded. The astronomers looked deep into the past. They found supernova that exploded billions of years ago. They expected to see the expansion slowing down. They expected the distant universe to be expanding faster than the nearby universe, showing that gravity was applying the brakes over time. Instead, they found the impossible. The distant supernovae were dimmer than they should have been. They were farther away than the math of a slowing universe allowed. The data was undeniable, yet it defied all physical intuition. The universe was not slowing down. It was not coasting. It was speeding up. Somewhere around 5 or 6 billion years ago, a mysterious switch was flipped. The brake pedal was released, and a gas pedal was pressed to the floor. The galaxies are not just drifting apart, they are fleeing from each other. The space between the clusters is growing at an accelerating rate. The universe is taking a breath that never ends, an inhalation that gets faster and deeper with every passing second. We call the cause of this acceleration dark energy. But just like dark matter, the name is a mask for our ignorance. It is a placeholder for a mystery that constitutes the majority of our reality. When we do the accounting, when we slice the pie of the universe, the numbers are staggering. Normal matter, the stars, the planets, the gas, you, me, the book on your shelf, makes up less than 5% of the cosmos. Dark matter, the invisible skeleton we just explored, makes up about 27%. And the rest, the remaining 68% of the universe, is dark energy. This means that the dominant stuff of existence is not matter at all. It is not even the heavy, clumping ghost of dark matter. It is a smooth, pervasive, invisible energy that fills every inch of empty space. It is the energy of the void itself. To understand how strange this is, we must look at the nature of nothing. In our daily lives, we think of empty space as a stage, a passive container where events happen. If you remove the furniture from a room, you have an empty room. If you pump the air out of a jar, you have a vacuum. We think of this vacuum as zero. No mass, no energy, no influence. But in quantum physics, there is no such thing as zero. The vacuum is not empty. It is seething. It is alive. It is a bubbling froth of virtual particles, popping in and out of existence, borrowing energy from the void and paying it back in a fraction of a nanosecond. The fabric of space-time itself has an intrinsic energy, a cost of existence. This is what Albert Einstein once called the cosmological constant. He originally included it in his equations to keep the universe static, to stop gravity from crushing it. When Edwin Hubble discovered the universe was expanding, Einstein deleted the constant, calling it his biggest blunder. But it turns out Einstein's blunder was actually a prophecy. There is an energy inherent to space, and this leads to a mechanism that is both simple and terrifying. Matter gets diluted. If you have a box of gas and you double the size of the box, the gas becomes half as dense. The atoms spread out. Dark matter behaves the same way. As the universe expands, the gravitational pull of the dark matter weakens because the particles get further apart. But dark energy is a property of space itself. It does not get diluted. If you double the amount of space, you double the amount of dark energy. It is constant per cubic inch. So, as the universe expands, it creates more space. That new space contains new dark energy. That new dark energy pushes the universe to expand faster. The faster expansion creates even more space. which creates even more dark energy, which causes even faster expansion. It is a runaway feedback loop. It is a self-feeding engine of isolation. Gravity is trying to pull the galaxies together, but its strength is fading as the distances grow. Dark energy is pushing them apart, and its strength is growing as the volume of the universe increases. About 5 billion years ago, the lines crossed. The density of matter dropped below the density of dark energy, and the anti-gravity push took over. We are now living in the era of dark energy dominance. We are riding the crest of a wave that is carrying everything away from everything else. This realization brings a profound sense of cosmic melancholy. We are living in a time of breakup. The local group of galaxies, our Milky Way, Andromeda, and the small dwarfs orbiting us, are bound tightly enough by gravity to stay together. We will merge, as we discussed, into a single island. But every other galaxy, every other cluster, every other light in the sky is destined to leave us. Imagine a future astronomer living on a planet orbiting a star in the merged Milkomeda galaxy, 100 billion years from now. By then, the expansion will have accelerated to such a degree that all the other galaxies will have been pushed beyond the cosmic horizon. The space between us and them will be expanding faster than the speed of light. Their light will never be able to reach us again. They will have vanished from the observable universe. That future astronomer will look up at the sky and see only the stars of their own galaxy. They will see a static, lonely island in an eternal, empty void. They will have no evidence of the Big Bang. They will have no evidence of the other 2 trillion galaxies that once filled the sky. They will construct a physics that says the universe is simple, small, and solitary. They will be wrong, but they will have no way of knowing it. The evidence of the grand, interconnected cosmos we see today will have been erased by the relentless push of dark energy. We are living in a privileged moment. We are living in the golden age of cosmology, the brief window in the history of the universe where the light from the distant past can still reach us. But the expansion is clear enough to be measured. We can see the galaxies before they leave. We can see the glow of the beginning. We are the witnesses to the truth before the curtain falls. But what is the nature of this push? Is it a gentle stretching, or is it a violent tearing? This depends on the specific properties of dark energy, something physicists call the equation of state. If dark energy is truly a cosmological constant, a steady energy of the vacuum, then the universe will expand forever, colder and darker. But the fabric of space will remain intact. But there is a darker possibility. If the strength of dark energy increases over time, a scenario called phantom energy, then the future is violent. This leads to the Big Rip. In this scenario, the repulsive force becomes so strong that it eventually overcomes not just the gravity between galaxies, but the gravity within galaxies. It would tear the Milky Way apart. Then it would overcome the gravity of solar systems, tearing the Earth away from the Sun. Then it would overcome the electromagnetic force, tearing electrons from atoms. And finally, in the last fraction of a second, it would overcome the strong nuclear force, ripping the very protons and neutrons apart. The universe would end in a shredding of the fabric of reality itself. Fortunately, our current measurements suggest that dark energy is constant. We are likely safe from the Big Rip. We are headed instead for the Big Freeze, or the heat death. It is a quieter, slower end, but one that is just as final. As we drift in the mental space of this acceleration, try to visualize the space in your room again. We often think of nothing as empty, But now you know that every cubic centimeter of the air around you, every gap between the atoms in your body, is filled with this mysterious, expansive potential. The vacuum is pushing. It is subtle here, overpowered by the gravity of the earth and the chemical bonds of your body. You do not feel yourself expanding because the electromagnetic force holding your atoms together is trillions of times stronger than dark energy on small scales. But on the scale of the cosmos, where the spaces are vast and the other forces are weak, the vacuum wins. The universe is becoming more nothing every day, and that nothing is powerful. There is a philosophical parallel here to the human condition. We often fear emptiness. We fill our silence with noise, our schedules with tasks, our minds with distractions. We treat space as something that needs to be occupied. But the universe tells us that space has its own power. The void is not a lack of something. It is a presence. It is the driver of destiny. The acceleration of the universe also challenges our sense of control. We like to think that with enough time and technology, we could explore everything. We could build ships to visit every galaxy. But dark energy sets a hard limit. There are places in the universe that we can never reach, no matter how fast we travel. Even if we moved at the speed of light, the space between us and the distant galaxies is creating itself faster than we can cross it. We are running on a treadmill that is speeding up. There are horizons that are forever closed to us. We are fenced in by the expansion. This realization can feel claustrophobic, or it can feel like a permission to focus. If we cannot conquer the infinite, we must cherish the finite. We must value the local group, the neighbors that gravity has managed to keep close. We must value the connection we have, because the universe is working hard to break it. Dark energy also raises the question of balance. Why is the number 68%? Why is the cosmological constant so small, yet just big enough to dominate? If dark energy had been slightly stronger in the early universe, it would have blown the gas clouds apart before they could collapse to form stars. There would be no galaxies, no suns, no life. If it had been slightly weaker, gravity might have crushed the universe back into a singularity billions of years ago. We seem to exist on a knife edge. The value of this vacuum energy is 120 orders of magnitude smaller than what quantum field theory predicts it should be. This is the worst prediction in the history of physics. Our math says the vacuum should be explosive, instantly tearing the universe apart. Our observations say it is a gentle, slow acceleration. Why the discrepancy? Why is the vacuum so surprisingly quiet? Some physicists suggest this is evidence of a multiverse. Maybe there are billions of other universes, bubbles in a vast cosmic foam. In some, the dark energy is strong and no stars form. In others, it is negative and the universe collapses. We live in this one with this specific, improbable value because this is the only kind of universe where observers can evolve to ask the question. We are here because here allows us to be. This is the Anthropic principle, the idea that the universe is tuned for life simply because we are alive to notice it. It is a dizzying thought. It suggests that our existence is selected from an infinite menu of failures. We are the winners of a cosmic lottery, living in the rare bubble where the push of the void and the pull of the gravity are perfectly balanced to allow for a 13 billion years summer of starlight. As you breathe in the dark room, feel the space around you again. It is ancient. It is expanding. The air you breathe is recycled star breath, but the space you occupy is primordial and ever-renewing. Dark energy is the breath of the void. It is the universe exhaling into the infinite. We have now set the stage for the final act. We have seen the stars born, the light travel, the mind perceive. and the dark matter hold the structure. Now we have seen the dark energy pushing the structure apart. What is the ultimate fate of this tug of war? What happens when the stars run out of fuel? What happens when the last black hole evaporates? In the next chapter, we will travel to the deep time. We will leave the era of humans, the era of the Earth, and even the era of the Sun. We will jump forward to the degenerate era, the black hole era, and the dark era. We will explore the concept of entropy, the arrow of time that points only in one direction. We will watch the universe wind down. We will ask if it is truly the end, or if, in the infinite rolls of the quantum dice, a new beginning is possible. But do not fear the end. Just as the darkness of the room allows you to sleep, the darkness of the future allows the universe to rest. The expansion is a clearing of the stage. The acceleration is a journey toward silence. And in that silence, there is a perfect mathematical peace. Rest now. You are safe in the gravity well of Earth, protected by the atmosphere, warmed by the sun, held by the dark matter, and carried gently into the future by the expanding breath of the cosmos. The universe is vast, and you are a part of its unfolding story. Have you ever accidentally knocked a ceramic mug off a table and watched it shatter on the floor? In that split second of destruction, you witnessed one of the most fundamental and unforgiving laws of the universe. The mug was once an ordered structure, a collection of atoms arranged in a precise, useful shape. When it hit the ground, that order was violently converted into disorder. The shards scattered. The energy of the fall became sound and heat. You can stare at the broken pieces for 1,000 years, but they will never spontaneously jump back up, reassemble themselves, and land perfectly on the table. The movie of reality only plays in one direction. We can turn an egg into an omelet, but we cannot turn an omelet back into an egg. We can burn a log into ash, but we cannot turn ash back into a log. This is the arrow of time. It points relentlessly from the past to the future, from order to disorder, from complexity to simplicity. Physicists call this entropy. It is the measure of randomness in a system. The second law of thermodynamics states that in a closed system, and the universe is the ultimate closed system, entropy must always increase. The universe is slowly, inexorably unwinding. It started in a state of extremely low entropy, a tight knot of perfect order at the Big Bang, and it has been unraveling ever since. Every star that burns, every engine that turns, every thought you think creates a little bit more disorder, adding to the cosmic ledger of chaos. We are riding a slide that goes only down. So, where does the slide end? If we follow the arrow of time to its ultimate conclusion, what lies at the bottom of the hill? In this chapter, we must cast our minds forward, past the era of humans, past the era of the Earth, and even past the era of the Sun. We are going to voyage into deep time. We are going to explore the eras of the universe that are so distant, so alien, and so vast that they make the 13.8 billion years of history we have experienced so far look like a single tick of a clock. We are moving toward the great silence. The first milestone on this road to eternity is the end of the stelliferous era, the age of stars. We are currently living in the high summer of this age. The universe is blazing with light. Galaxies are factories churning out new suns. But, as we learned in the previous chapter, the raw material for this industry, the hydrogen gas, is finite. The universe is not refilling the tank. Every star that is born locks away a little bit of gas forever in its dead core. Every galaxy that merges uses up its reserves in a burst of star formation, slowly, Steadily, the lights are going out. Astronomers estimate that in about 100 trillion years, the last star will be born. It will likely be a small, frugal red dwarf huddled in the dark of a dying galaxy. When that final star ignites, the era of creation will officially end. No new fire will ever be lit again. The universe will have used up its potential. From that moment on, the cosmos will be a place of dying, not living. The massive blue stars will have vanished long ago. The yellow suns like ours will have bloated into red giants and then shrunken into white dwarfs. The only survivors will be the red dwarfs, those tiny, efficient stars that sip their fuel. They will guard the light for trillions of years, but eventually, even they will falter. They will exhaust their hydrogen. They will not explode. They do not have the mass for drama. They will simply fade. They will shrink, turn blue for a brief, final hot spell, and then cool down into white dwarfs. One by one, the galaxies will go dark. If you were an observer in this distant future, you would see the stars blinking out like candles in a drafty cathedral. The night sky, once a tapestry of diamonds, will become a void. The last red dwarf will sputter and die, and the universe will plunge into a darkness that will never be lifted. This marks the beginning of the degenerate era. The universe will be a graveyard of stellar corpses. It will be populated by brown dwarfs, failed stars, white dwarfs, dead suns, neutron stars, dead giants, and black holes, dead monsters. These are the degenerate objects, matter crushed into states of incredible density. It will be a cold, dark place, but not completely dead. Occasionally in the dark, two white dwarfs might spiral into each other and collide, sparking a type Ia supernova, a brief, lonely flare of light that illuminates the nothingness for a few weeks before fading back to black. Occasionally, a brown dwarf might drift too close to a black hole and be torn apart, creating a momentary accretion disk of glowing gas. But these will be rare, ghostly events in a universe of silence. As the eons drag on, and we are talking about time scales of quadrillions of years now, gravity will continue its work. The galaxies themselves will begin to dissolve. Without the visible mass of living stars to define them, the stellar corpses will interact gravitationally. They will swing past each other in the dark. In these encounters, some objects will be flung out of the galaxy entirely, ejected into the intergalactic void to drift alone forever. Others will lose energy and sink toward the center, feeding the supermassive black hole lurking there. Over time, every galaxy will essentially evaporate. It will be reduced to a central supermassive black hole surrounded by a halo of scattered, lonely corpses drifting away into the expansion. But the decay does not stop there. We tend to think of matter, atoms, protons, neutrons, as eternal. We think of diamonds as forever, but physics suggests that even the proton, the building block of the atomic nucleus, may not be immortal. Many grand unified theories of particle physics predict that protons are unstable. They just have an incredibly long half-life, perhaps 10 to the power of 34 years. That number is impossible to visualize. 10 to the 34. If you wrote a 0 on every atom in the observable universe, you would run out of atoms before you finished writing the number. But in the vastness of deep time, even this eternity eventually passes. There will come a time when the matter itself begins to rot. The white dwarfs, the neutron stars, the planets, the dead rocks, they will all begin to dissolve. The protons inside their atoms will decay into positrons and pions, which will then decay into gamma rays. The solid objects of the universe will simply melt away into radiation. The degenerate era will end when the last piece of degenerate matter has evaporated. The diamonds in the sky will turn to ghost light. The planets will turn to energy. The physical structure of the universe will be erased. This brings us to the black hole era. The only things that can survive proton decay are the black holes. They are not made of matter. They are made of gravity. They are pure geometry. In a universe where all the stars and planets have melted into radiation, the black holes will be the undisputed kings. They will drift through a universe of photons and neutrinos, enormous and silent, hoarding their mass. But even kings must die. Stephen Hawking, one of the greatest minds of our time, discovered that black holes are not truly black. Due to quantum effects at the event horizon, the edge of the abyss, they slowly leak radiation. Virtual particles pop into existence near the edge. One falls in, the other escapes. To an outside observer, it looks like the black hole is emitting a faint glow of heat. We call this Hawking radiation. For a massive black hole, this process is agonizingly slow. A black hole the mass of our sun would take 10 to the 67 years to evaporate. A supermassive black hole, billions of times heavier, would take 10 to the 100 years. This is a Google years. It is a span of time so vast that the entire history of the stars, from the first ignition to the last fading red dwarf, is less than a billionth of a percent of the total timeline. But the clock is ticking. Slowly, surely, the black holes will shrink. As they get smaller, they get hotter. They radiate faster. In their final moments, after eons of dark silence, they will explode. They will release all their remaining mass in a blinding flash of gamma rays and particles. It will be the last firework display of the cosmos. One by one, the black holes will detonate and vanish. And then we enter the dark era, the final chapter, the heat death. When the last black hole has evaporated, there will be no matter left, no gravity to hold anything together. The universe will be a thin soup of photons, neutrinos, and perhaps electrons and positrons, drifting so far apart that they never meet. The expansion of the universe, driven by the dark energy we discussed, will have stretched space so much that every particle will be alone in its own observable universe. The temperature will approach absolute zero, not just cold, but the absence of heat. The entropy will be maximized. The energy of the universe will be spread out perfectly evenly. There will be no gradients, no hot spots, no cold spots, no flow of energy. And without a flow of energy, nothing can happen. Time, in a sense, will cease to have meaning. If nothing changes, if nothing moves, if one moment is identical to the next for eternity, does time even exist? The universe will have returned to a state of void. It started as a singularity of infinite energy, and it ends as an infinity of zero energy. It is a perfect symmetry, from nothing to something to everything, and back to nothing. This concept, the heat death, strikes a chord of primal fear in the human heart. It feels like a tragedy. It feels like a waste. We look at the complexity of our world, the music, the love, the architecture, the biology, and we mourn the idea that it will all eventually be erased, leaving not even a memory behind. If the universe ends in silence, what was the point of the noise? But I want to offer you a different perspective, a gentler way to look at the inevitable dark. Think of a song. A beautiful piece of music has a beginning, a middle, and an end. The fact that the song ends does not make the music meaningless. The beauty is in the flow, in the temporary disturbance of the silence. If the song went on forever, it would lose its structure. It would become noise. The silence that follows the final note is part of the composition. It is the frame that gives the picture its definition. The heat, death, is the silence after the song. It is the rest that follows the exertion. The universe is expending incredible energy right now to create stars, galaxies, and life. It is doing something, and like all things that do work, it must eventually rest. The dark era is the eternal sleep of a cosmos that has fulfilled its potential. Furthermore, this timeline teaches us something profound about us. We are living in the stelliferous era. We are living in the one tiny, precious sliver of time where the universe is hospitable to life. We are living in the Goldilocks moment of eternity. We are not late, and we are not early. We are right on time. If we had been born in the early universe, it would have been too hot, too chaotic, too radioactive. If we had been born in the degenerate era, there would be no suns to warm us, no planets to stand on. We exist in the only window where complexity is possible. We are the eyes of the universe during its brief, brilliant awakening. This makes our existence infinitely more valuable. We are not just random accidents. We are the rare witnesses. We are the memory of the cosmos. If the universe is destined to forget, then our act of remembering now becomes a sacred duty. When you look at a flower, when you love a person, when you learn a fact, you are defying the entropy. You are creating a pocket of order and meaning in a universe that is sliding toward disorder. You are holding back the dark, if only for a moment. And who knows? Physics is a story that is still being written. We talk about the heat-death based on the laws we understand today. But our understanding is incomplete. We do not know the true nature of dark energy. Does it reset? Does it cycle? Some theories suggest that in the infinite span of the vacuum, quantum fluctuations could spontaneously trigger a new Big Bang. A baby universe could pinch off from the dead fabric of the old one, starting the clock all over again. Perhaps the universe is not a line, but a circle. Perhaps the heat-death is just the winter before a new cosmic spring. We cannot know. We are limited by our view from inside the bubble. But as you lie here, safe in the stelliferous era, bathed in the warmth of a living star, surrounded by the ordered matter of your home, feel the preciousness of this low-entropy state. You are a miracle of structure. You are a defiance of the chaos. The atoms in your body are holding hands, resisting the drift, working together to create the experience of you. The arrow of time pushes us forward, yes, it ages us. It breaks the teacup, it burns the star, but it also allows for change. Without the flow of time, there would be no growth, no learning, no story. A static universe would be eternal, but it would be frozen. We pay for life with mortality. We pay for existence with entropy. It is a fair trade. The ghost of the future is silent, but it is not malicious. It is simply the nature of water to seek the lowest point, and it is the nature of energy to seek the widest space. The universe is exhaling. Let it breathe. In the next chapter, we will retreat from the brink of the end. We have looked at the very large and the very distant. Now, let us look at the very mysterious connection between this cosmic drama and the mind that perceives it. We will explore the anthropic principle in depth. Why is the universe tuned for life? Is it luck? Is it design? Or is it an illusion? We will look at the idea that consciousness might not be a byproduct of the universe, but a fundamental component of it. We will ask, could the universe exist without you? Rest now in the fleeting, beautiful moment of the now. The stars are still shining. The black holes are still eating. The protons are still stable. You have trillions of years before the lights go out. There is plenty of time to dream. We have arrived at the final threshold of our journey. We have traveled from the crushing pressure of the solar core to the silent, expanding voids of the deep future. We have watched the birth of light and the death of stars. We have peered into the machinery of our own eyes and touched the invisible skeleton of dark matter. But there is one final mystery that binds all of these disparate threads together. It is the mystery of the observer. It is the mystery of you. Throughout this odyssey, we have treated the universe as a vast external stage, a place of fire and gravity that exists independently of us. We have assumed that the stars would still shine and the black holes would still spin, even if there were no eyes to see them. But modern physics has led us to a strange and unsettling doorway. It forces us to ask a question that borders on the spiritual. Is the universe fine-tuned for us? Or are we simply a happy accident in a cold and indifferent void? To understand this, we must look at the dashboard of the universe. Imagine that the cosmos is a machine with a set of dials and sliders that control the fundamental laws of nature. One dial controls the strength of gravity. Another controls the charge of the electron. Another controls the strength of the nuclear force that binds atoms together. Another controls the expansion rate of space, the dark energy we discussed. When physicists measure the settings of these dials, they find something that makes them tremble. The settings are not random. They are precise. They are tuned to an exquisite degree of accuracy that defies statistical probability. Take gravity, for example. If the dial for gravity had been turned up just a tiny fraction, if it were slightly stronger, the universe would have collapsed back into a fireball shortly after the Big Bang. No stars, no galaxies, no life. Just a brief, hot flash, and then silence. If the dial had been turned down just a tiny fraction, if gravity were slightly weaker, the gas clouds would never have condensed. They would have drifted apart forever. No stars would have ignited. The universe would be a cold, dark, expanding mist of hydrogen. Take the strong nuclear force. If it were 2% stronger, all the hydrogen in the primordial universe would have fused into helium in the first few minutes. There would be no hydrogen left to fuel the stars. There would be no water, H2O. If it were 2% weaker, protons would not stick together at all. There would be no atoms heavier than hydrogen, no carbon, no oxygen, no iron, no complexity. The list goes on. The mass of the electron, the speed of light, the ratio of matter to antimatter. Every single constant seems to be balanced on a knife edge. It is as if the universe knew we were coming. It is as if a grand designer sat at the control panel and carefully adjusted every parameter to ensure that 13.8 billion years later, a conscious being could sit in a room and wonder about it. We call this the Anthropic principle. It states that the universe must have properties that allow for the existence of observers, because if it didn't, we wouldn't be here to notice it. There are two ways to interpret this. The first is the weak anthropic principle. It is a statement of selection bias. It says, we shouldn't be surprised that we see a universe capable of supporting life, because if the universe were different, we wouldn't be here to be surprised. It is like a lottery winner asking, why did I win? The answer is, because if you hadn't won, you wouldn't be standing on the stage holding the check. The billions of losers are not asking the question. This leads to the multiverse theory we touched upon. Perhaps the universe is not unique. Perhaps there is an eternal ocean of inflation, a fast expanding foam of spacetime that is constantly bubbling off new pocket universes. In this cosmic foam, Every bubble has different settings on its dashboard. In bubble A, gravity is too strong. It collapses. In bubble B, the electron is too heavy. Chemistry is impossible. In bubble C, dark energy tears everything apart. These are the sterile universes. They are vast, dead, and unwitnessed. But in bubble D, our bubble, the numbers came up right. The lottery was won. The stars ignited, the carbon formed, and the eyes opened. We are here not because we are special, but because we are the inevitable survivors of a cosmic game of chance, played on an infinite scale. This explanation is scientific. It relies on probability, but it leaves many people feeling cold. It suggests that our existence is just a statistical fluke, a random success in a sea of failure. So, let us consider the strong anthropic principle. This idea is bolder. It suggests that the universe must produce conscious observers at some stage in its history. It implies that consciousness is not an accidental byproduct of matter, but a fundamental goal of the cosmos. It suggests that a universe without a mind to perceive it is not really a universe at all. Think back to the quantum mechanics we discussed in the beginning. The photon, that is both a wave and a particle, until it is measured. We learned that the act of observation collapses the wave function, turning possibility into reality. Some physicists, like the visionary John Archibald Wheeler, took this to its ultimate conclusion. He proposed the idea of the participatory universe. He drew a famous diagram, a large U shape, representing the timeline of the universe. One arm of the U is the Big Bang. The other arm is the present day. At the end of the timeline, there is an eye, a giant eye, looking back at the beginning. Wheeler was suggesting that by looking at the universe, we are actually creating it. We are the mechanism by which the universe becomes real. The photons from the Big Bang have been traveling for billions of years in a state of quantum superposition, a fuzzy haze of maybe. But when they hit your telescope, when they hit your eye, they become definite. You are anchoring the past. You are the final piece of the puzzle that locks reality into place. This is a profound shift in perspective. You are not a tiny, insignificant speck crawling on a rock in a forgotten corner of a dark galaxy. You are the awakened mind of the cosmos. You are the universe's way of knowing itself. The hydrogen atoms that were forged in the Big Bang have spent 13 billion years assembling themselves into a structure, your brain, that can look back at the hydrogen and say, I see you. The separation between subject and object, between observer and observed, is an illusion. We are the same thing. We are the mirror that the nothingness built so it could see its own face. So, as we close this script, let us trace the full circle of the photon's journey one last time. It began in the crushing dark of the sun's core, born from the fusion of protons. It fought its way to the surface for 100,000 years. It flew across the cold void for 8 minutes. It scattered in the blue sky. It entered the pupil of your eye. It struck the retina. It became electricity. It became a thought. And what was the thought? The thought was wonder. The thought was beauty. The thought was, I exist. The photon's journey did not end on the retina. It ended in your soul. The energy that was released by the star has been transmuted into the energy of consciousness. You have eaten the light, and you have turned it into meaning. This is the hidden secret in the core of the photon. It was never just a packet of energy. It was a letter, a message sent from the dawn of time, waiting for a recipient. And you are that recipient. This realization should bring you a deep, abiding peace. In our daily lives, we often feel disconnected, anxious, or lonely. We worry about our small problems, our deadlines, our relationships. We feel separate from the world. But the science tells a different story. It tells us that we are woven into the very fabric of space-time. We are made of the same fields, the same forces, the same dust as the stars. We are supported by the same dark matter. We are carried by the same expansion. You belong here. You fit. The universe has spent 13.8 billion years preparing this moment for you. The temperature is right. The gravity is right. The chemistry is right. You are exactly where you are supposed to be, doing exactly what you're supposed to be doing, witnessing the glory of it all. The mystery of the universe is not a problem to be solved. It is a reality to be experienced. We will never know all the answers. We may never catch the dark matter particle. We may never know what happened before the Big Bang. We may never know if the multiverse is real. And that is okay. In fact, it is beautiful. If we knew everything, the journey would be over. The wonder would fade. The mystery is the fuel of the human spirit. It is what drives us to build telescopes, to write poems, to dream. The unknown is not a frightening void. It is an invitation. It is a call to keep exploring, to keep asking, to keep looking up. So, tonight, as you drift towards sleep, do not think of the dark as an empty space. Think of it as a canvas. Think of the silence as a presence. You are a sleepy scientist, a member of a quiet, global community of minds who are daring to look into the abyss and find beauty there. We are all travelers on this rock, spinning through the dark, protected by a bubble of air, warmed by a middle-aged star, holding on to each other in the gravity of love and curiosity. The journey is far from over. There are infinite chapters left to write. There are nebulae we have not seen, particles we have not named, and thoughts we have not yet thought. I invite you to stay on this journey with me. Let us continue to peel back the layers of reality, not to conquer them, but to appreciate them. Let us continue to ask the questions that have no easy answers, for those are the only questions worth asking. If this exploration of the photon has brought you a moment of peace, a moment of aha, or just a moment of quiet distraction from the noise of the world, then our mission is accomplished. The universe is vast, but it is not lonely, because we are exploring it together. Sleep well, knowing that the stars are keeping watch. Sleep well, knowing that your atoms are eternal. Sleep well, knowing that you are the universe waking up to dream. Until the next time we meet in the starlight, keep your eyes open to the wonder and your mind open to the mystery.